Picture this, a galaxy out in the vast darkness of space that doesn't play by the rules. Centaurus A, just 11 million light-years from Earth, is one of the most bizarre and mysterious galaxies we've ever discovered. It's like the universe took everything we thought we knew about galaxies and threw it out the window. At its heart lurks a supermassive black hole spewing jets of energy across space, while strange dust lanes twist through its center like cosmic ribbons. And that's just the beginning. Today, we're going to count down 50 of the most mind-bending phenomena hidden within Centaurus A, from ghostly stellar streams to unexplained gamma-ray bursts, from missing star clusters to secrets locked in its dark matter halo. Each one of these cosmic oddities challenges what we thought was possible in our universe. So get ready, because we're about to take a journey into one of space's greatest mysteries, where every discovery raises new questions about how galaxies really work. Trust me, by the time we reach phenomenon number 50, you'll never look at the night sky the same way again. Now let's plunge straight into the heart of Centaurus A, where the first and perhaps most jaw-dropping phenomenon lies in wait. At the very core of this galaxy, a monster lurks, a supermassive black hole with a mass 55 million times that of our Sun. To put that into perspective, imagine squeezing 55 million suns into a single point of unimaginable density. The gravitational pull of this beast is so intense that not even light can escape its clutches once it crosses the event horizon. But this black hole isn't just sitting quietly. It's active, ravenous, and shaping the entire galaxy around it in ways that defy expectations. One of the most astonishing features of this cosmic giant is its twin jets, colossal beams of energy that shoot out from its poles at nearly the speed of light, stretching hundreds of thousands of light-years into space. These jets are so powerful that they glow brightly in radio waves, creating vast lobes visible in telescope images. Picture a cosmic blowtorch carving through the galaxy, heating and pushing gas and dust aside with incredible force. The energy released is so immense that it disrupts star formation, warps the galaxy's structure, and even influences its dark matter halo. Then there's the accretion disk, a swirling maelstrom of superheated gas, dust, and doomed stars spiraling toward oblivion. As material gets pulled in, friction heats it to millions of degrees, causing it to glow intensely in X-rays. This disk isn't just feeding the black hole. It's a powerhouse fueling those massive jets and generating magnetic fields strong enough to twist space itself. Astronomers have observed fluctuations in this disk, suggesting that the black hole doesn't feed steadily but in violent, erratic bursts, like a cosmic predator gulping down its prey. What makes this black hole even more fascinating is its influence on the entire galaxy. Normally, galaxies like our Milky Way have orderly rotations with stars and gas moving in predictable patterns. But Centaurus A, it's chaotic. The black hole's jets have punched through the galaxy, stirring up gas clouds, distorting star-forming regions, and even flinging stars into wild orbits. Some researchers think past eruptions might have blown away entire sections of the galaxy's gas, leaving behind ghostly cavities. Yet despite all this destruction, the black hole also plays a creative role. Shockwaves from its jets compress nearby gas, sometimes triggering new star birth in odd places. It's a cosmic paradox, destruction and creation happening side by side, all orchestrated by this gravitational titan. To truly grasp its scale, radio telescopes like the Very Large Array have captured stunning images of its jet structures, revealing intricate knots and bends that suggest magnetic fields are shaping their path. These observations aren't just for show, they help scientists understand how black holes grow, how they impact their galaxies, and even how they might shape the universe over billions of years. So as we peel back the layers of Centaurus A, this supermassive black hole stands as the first and perhaps most defining mystery. a reminder that even in the cold vastness of space, the most extreme forces are hard at work, rewriting the rules of galactic evolution. Now let's shift our gaze from the monstrous black hole at the center of Centaurus A to another striking feature: the bizarre, warped dust lanes that slice across the galaxy like cosmic scars. These thick, twisting bands of dust aren't just decorative, they're the aftermath of a violent collision, a celestial crash that reshaped this galaxy forever. Picture this: millions of years ago, a smaller galaxy careened into Centaurus A, sending shockwaves through its structure. The impact didn't just scatter stars, it sent vast clouds of gas and dust spiraling inward, where they were twisted and stretched by the galaxy's gravity. Today, these dust lanes snake across Centaurus A in chaotic, uneven patterns, some so dense they block the light from stars behind them. It's as if the galaxy is wearing a dark, tangled veil, hiding parts of itself from view. What's truly fascinating is how these dust lanes aren't just passive remnants, they actively shape the galaxy's appearance and behavior. Their uneven distribution creates pockets where star formation is stifled, as the thick dust absorbs the energy needed for new stars to ignite. In other areas, the dust acts like a cosmic sieve, filtering and redirecting light in ways that make Centaurus A look patchy and fragmented when viewed through optical telescopes. But here's where it gets even more intriguing. The dust lanes aren't just random debris, they're clues to the galaxy's violent past. Their twisted paths suggest they've been yanked and warped by gravitational forces, possibly even by the supermassive black hole's immense pull. Some astronomers believe these lanes are still settling, slowly adjusting to the galaxy's turbulent environment. Others think they might be fueling the black hole itself, funneling material toward the center like cosmic conveyor belts. And let's not forget the role of perspective. From Earth, we see these dust lanes almost edge-on, which amplifies their dramatic effect. If we could view Centaurus A from above, the lanes might appear more like a spider's web, a delicate but intricate network of dark threads woven into the galaxy's brighter stars and gas. What's clear is that these dust lanes aren't just static features. They're dynamic, evolving structures that tell the story of Centaurus A's past collisions and ongoing transformations. They contribute to the galaxy's chaotic beauty, making it one of the most visually striking objects in the night sky. So the next time you see an image of Centaurus A, remember, those dark, swirling lanes aren't just dust. They're the fingerprints of a cosmic catastrophe, frozen in time but still shaping the galaxy's destiny. Leaving behind the warped dust lanes, let's zoom out to witness one of Centaurus A's most colossal features, its gigantic radio lobes. These are not just faint whispers in the cosmos, they're roaring signals stretching millions of light years into intergalactic space, dwarfing the galaxy itself. Imagine two vast, ghostly balloons of radio waves, each billowing outward from the galaxy's core, forming a structure so immense it could span the distance between our Milky Way and Andromeda many times over. These lobes are cosmic megaphones broadcasting the violent energy of Centaurus A's supermassive black hole. Here's how it works. At the galaxy's core, the black hole doesn't just devour matter. It launches twin jets of charged particles at nearly the speed of light. These jets, channeled by intense magnetic fields, plow through the surrounding gas and dust until they slam into the sparse material outside the galaxy. The collision creates shock waves, heating the gas and accelerating electrons to extreme energies. As these electrons spiral around magnetic field lines, they emit radio waves, painting the lobes with their eerie glow. What's remarkable is how these lobes act as a fossil record of the black hole's activity. Their sheer size tells us these jets have been firing for tens of millions of years, maybe longer. Yet they're not static. Astronomers have spotted knots and filaments within the lobe's turbulent structures, suggesting the black hole's outbursts aren't steady but come in violent bursts. Some regions appear brighter, hinting at recent surges of energy, while others fade like echoes of ancient eruptions. But the lobes aren't just about the past, they're reshaping the galaxy's future. By injecting energy into the surrounding intergalactic medium, they prevent nearby gas from cooling and collapsing to form new stars, effectively putting a cosmic brake on galaxy growth. This feedback mechanism is crucial to understanding why some galaxies, like Centaurus A, don't grow as large as their neighbors despite their violent cores. And here's a twist: the lobes aren't perfectly symmetrical. One stretches farther than the other, likely because the jets encountered uneven resistance, perhaps from the debris of past collisions or the galaxy's own warped structure. This asymmetry is a goldmine for researchers, offering clues about the environment surrounding Centaurus A and how it's evolved over eons. Studying these radio lobes is like reading a cosmic diary. They reveal how black holes and galaxies co-evolve, how energy from the core can influence an entire galactic neighborhood, and even how the universe recycles matter on the grandest scales. So when you see images of Centaurus A's radio lobes, remember, those faint, sprawling structures are more than just relics. They're the heartbeat of a galaxy, pulsing with stories of creation and destruction written in radio waves. Now, shifting our focus from the sprawling radio lobes, let's turn our attention to something far more elusive yet equally fascinating: the mysterious dark matter halo surrounding Centaurus A. While we can't see dark matter directly, its presence is felt through the gravitational tug it exerts on everything around it. Picture this: the galaxy is like a ship sailing through an invisible ocean where the waves, dark matter, guide its course, shaping its destiny in ways we're only beginning to understand. The first clue to this hidden halo comes from the way Centaurus A's stars move. Normally, stars orbiting a galaxy should slow down as you move farther from the center, much like planets in our solar system. But here's the twist: observations show stars at the galaxy's outer edges whizzing around just as fast as those near the core. This unexpected speed implies there's something unseen adding extra gravity, something that doesn't emit light but has mass. That's where dark matter steps in, wrapping the galaxy in a massive, invisible cocoon that keeps those stars from flying off into the void. Gravitational lensing offers another glimpse into this enigma. When light from distant galaxies passes near Centaurus A, it bends slightly as if the galaxy were a lens warping spacetime. But here's the catch: the bending is far stronger than the visible matter alone can explain. The only way to account for this extra distortion: a colossal halo of dark matter far larger than the galaxy itself, bending light with its immense gravitational pull. It's like seeing the shadow of something vast lurking just beyond our sight. What makes this halo even more intriguing is how it connects to Centaurus A's violent history. Simulations suggest that when galaxies collide, their dark matter halos merge, creating a messy, extended structure. Given Centaurus A's past mergers, its halo might be littered with clumps and streams of dark matter, remnants of its cosmic feast. Yet, detecting these clumps is a challenge as they leave no light trail. Instead, astronomers hunt for subtle anomalies in star motions or lensing patterns, piecing together the halo's ghostly architecture. And here's the real kicker: this halo isn't just a passive bystander. It's thought to act like a scaffold, holding the galaxy together while its black hole and jets stir up chaos. Without it, Centaurus A's outer stars and gas would have scattered long ago, torn apart by the violence at its core. So while dark matter remains one of the universe's greatest mysteries, its fingerprints are all over this galaxy, silently shaping its past, present, and future. As we peer deeper into Centaurus A's secrets, the dark matter halo stands as a reminder of how much we still don't see, and how much more there is to discover. It's a cosmic detective story where every clue pulls us closer to understanding the invisible forces that rule the cosmos. Now, let's step away from the invisible grip of dark matter and into the haunting aftermath of Centaurus A's cosmic feast, the stellar tidal streams. These ghostly trails of stars are like breadcrumbs scattered across the galaxy, telling the tale of smaller galaxies that wandered too close and were torn apart by Centaurus A's immense gravity. Imagine a river of stars flowing silently through space, their very presence a record of destruction and survival. These streams aren't just random scatterings. They're the remnants of galaxies that once orbited Centaurus A, only to be pulled apart over billions of years. As the smaller galaxy was stretched and shredded, its stars were flung into long, delicate arcs, tracing the path of its final orbit. It's a process akin to unraveling a ball of yarn, with each strand remaining visible long after the original shape is gone. Astronomers call this tidal disruption, and Centaurus A is a master of it, with multiple streams weaving through its outskirts like cosmic graffiti. What makes these streams so valuable is their ability to act as time capsules. By mapping their positions and motions, astronomers can reconstruct the history of Centaurus A's mergers, essentially reading its past meals like a galactic menu. For example, one prominent stream might trace back to a dwarf galaxy swallowed up 500 million years ago, while another could be the last gasp of a system devoured just 100 million years ago. The stars in these streams retain clues about their origins, such as their chemical composition, which often differs from Centaurus A's native stars. It's like finding foreign spices in a dish, hinting at the ingredients that went into it. But detecting these streams is no easy task. They're faint, spread thin across vast distances, and often drowned out by the brightness of Centaurus A itself. Advanced telescopes equipped with sensitive cameras have been key to spotting them, capturing light so dim it's like trying to see a candle flame from 1,000 miles away. Once identified, these streams offer more than just a history lesson. They also help scientists understand how galaxies grow. Centaurus A's streams confirm a long-held theory. Massive galaxies like this one build themselves by consuming smaller neighbors, a process astronomers poetically call galactic cannibalism. Here's where it gets even more intriguing. Some of these streams aren't just passive relics, they're still in motion, slowly being absorbed into Centaurus A's main body. Over time, their stars will mix with the galaxy's own, erasing the evidence of their origins. That's why these streams are so precious. They're fleeting snapshots of a violent process that's still unfolding. Without them, we'd have far fewer clues about how galaxies like Centaurus evolve into the giants we see today. So the next time you gaze at an image of Centaurus A, remember, those faint, wispy trails of stars aren't just decoration. They're the echoes of ancient collisions, the fingerprints of a galaxy that grew by devouring others. And as we study them, we're piecing together a story that spans billions of years, one where even the quietest corners of space hold secrets waiting to be uncovered. Now, shifting our gaze from the ghostly stellar streams, let's turn toward one of Centaurus A's most enigmatic features, its unusual gamma-ray emissions. Unlike most galaxies, Centaurus A stands out as a rare cosmic powerhouse, blazing with high-energy gamma rays that challenge our understanding of galactic behavior. These aren't just faint flickers, they're among the most energetic signals in the universe, and their presence here raises a compelling question: what's fueling them? The answer likely lies in the galaxy's monstrous jets, those vast beams of plasma shooting from its supermassive black hole at nearly the speed of light. As particles within these jets collide and twist through powerful magnetic fields, they're accelerated to unimaginable energies, a bit like cosmic pinballs ricocheting at full force. When these particles smash into surrounding gas or light, they can produce gamma rays, the same kind of radiation generated by the most violent explosions in the cosmos. What's fascinating is that Centaurus A's jets seem unusually efficient at this process, making it one of the brightest gamma-ray sources beyond our own galaxy. But the plot thickens. Some scientists speculate that dark matter might also play a role. If certain theoretical particles, like weakly interacting massive particles or WIMP, exist, they could collide and annihilate each other in Centaurus A's dense dark matter halo, releasing gamma rays in the process. While this idea is still speculative, it's tantalizing because it could mean we're glimpsing not just the fury of a black hole, but the invisible hand of dark matter itself. Imagine a single galaxy offering clues to two of the universe's greatest mysteries. Detecting these gamma rays isn't simple. They're absorbed by Earth's atmosphere, so telescopes like NASA's Fermi Gamma Ray Space Telescope must orbit above it to catch them. Through years of observations, Fermi has mapped Centaurus A's gamma-ray glow, revealing surprises. For instance, the emissions aren't just coming from the jets, they're also diffused across the galaxy's giant radio lobes, suggesting particle acceleration happens far from the black hole, in regions where the jets plow into intergalactic space. It's as if the galaxy is surrounded by an invisible particle accelerator, stretching millions of light years. What makes Centaurus A even more puzzling is how its gamma-ray output varies. Unlike steady sources, its emissions flicker unpredictably, hinting at chaotic processes within the jets. Some researchers think this could be due to clumps of material falling into the black hole, creating bursts of activity, while others propose instabilities in the jet's magnetic fields. Either way, it's a reminder that this galaxy is anything but quiet. It's a dynamic, ever-changing beast. So why does this matter? Gamma rays are messengers of extreme physics, and Centaurus A's ability to produce them so prolifically makes it a natural laboratory. By studying them, we're not just learning about one peculiar galaxy. We're testing fundamental theories about how particles reach such energies, how black holes influence their surroundings, and whether dark matter might leave traces in the light we observe. Every gamma ray we detect carries a piece of that puzzle, drawing us closer to understanding the invisible forces shaping our universe. As we continue unraveling Centaurus A's secrets, remember, what seems like a distant mystery today could be the key to tomorrow's breakthroughs. And with telescopes growing ever more advanced, who knows what other surprises this galaxy and others like it might reveal. Now, let's zoom in closer to the heart of Centaurus A, where its colossal jets reveal yet another layer of intrigue. These aren't just smooth, uniform beams of energy. Instead, they're riddled with bizarre, knotty structures that glow fiercely in X-rays like cosmic beads on a string. These tangled formations aren't just eye-catching, they're rewriting what we thought we knew about how black hole jets behave. At first glance, you might expect such jets to flow evenly, like water from a hose. But Centaurus A's jets are anything but orderly. High-resolution X-ray observations show them splintering into clumps and twists, with bright knots separated by fainter gaps. Some of these knots even appear to move over time, as if something is pushing or pulling them from within. The big question is why. One leading theory points to the jet's magnetic fields. Imagine squeezing a tube of toothpaste, but instead of paste, it's magnetic energy threading through the jet. If these fields become twisted or unstable, they could pinch the jet into these distinct clumps, creating shock waves that heat the material and make it glow in X-rays. It's like cosmic turbulence on a scale we can barely fathom. But here's the catch. Our models suggest jets should stabilize over long distances, smoothing out these knots. Centaurus A laughs at that idea. Its jets remain lumpy millions of light years from the black hole, defying expectations. Another puzzle is the sheer energy of these X-ray knots. Some shine brighter than entire star clusters, suggesting processes far more violent than simple magnetic pinching. Could there be hidden black holes or neutron stars within the jets, adding extra energy? Or perhaps the supermassive black hole at the center is injecting fresh surges of power at irregular intervals, like a cosmic engine sputtering to life. Either way, these knots are a glaring sign that our understanding of jet physics is incomplete. What makes this even more fascinating is how these structures interact with their surroundings. As the jets plow through Centaurus A's halo of gas, they create ripples like a speedboat churning water. These interactions might further fragment the jets, adding to their knotty appearance. But sometimes the opposite happens. The jets seem to carve out cavities in the gas, creating pockets where the knots brighten abruptly. It's a chaotic dance of pressure, heat, and magnetic forces, and we're only beginning to decode its steps. So, why should we care about lumpy jets in a distant galaxy? Because they're a cosmic stress test for our theories. If we can figure out why these structures persist, we might unlock secrets about how black holes channel energy across unimaginable distances and how they shape entire galaxies in the process. Centaurus A, with its defiantly knotted jets, is forcing us to rethink the rulebook, and in science, that's when things get truly exciting. As we peel back these layers, remember, every strange detail is a clue. And in a galaxy as wild as Centaurus A, there are always more clues waiting to be found. Now, here's something that might seem counterintuitive. In the chaotic heart of Centaurus A, where a monster black hole unleashes jets powerful enough to tear apart entire star systems, there are pockets of space where new stars are being born at a staggering rate. How does star formation thrive in what should be a cosmic war zone? Let's unravel this paradox. At first glance, you'd expect the black hole's fury to snuff out any chance of star birth. Its jets blast through the galaxy at nearly the speed of light, heating surrounding gas to millions of degrees and tearing apart molecular clouds before they can collapse into stars. Yet, observations reveal vibrant stellar nurseries, particularly along the edges of those very same jets and within the galaxy's twisted dust lanes. This isn't just a fluke, it's a cosmic balancing act. One key lies in the way shockwaves from the jets interact with cold gas clouds. While the jets do vaporize some material, they also compress other pockets of gas as they ram through the galaxy. Picture a snowplow pushing aside loose snow, piling it into dense mounds. Similarly, when the jet's shockwaves slam into cooler gas, they can squeeze it just enough to trigger gravitational collapse, the first step in star formation. In fact, some of the most intense star-forming regions in Centaurus are found right where these jets meet dense gas clouds, as if the black hole's violence is inadvertently creating the perfect conditions for new stars. Another factor is the galaxy's messy history of mergers. Centaurus A is a cannibal, having devoured smaller galaxies over billions of years. These collisions dragged in fresh supplies of cold gas, the raw material for stars, and stirred up the galaxy's structure. In the chaos, some gas pockets escaped the black hole's immediate wrath, settling into quieter regions where they could cool and fragment. This might explain why star formation isn't uniform, but instead flares up in specific areas like sparks in a windstorm. Then there's the role of magnetism. Centaurus A's jets are threaded with powerful magnetic fields, and these fields might do more than just shape the jets. They could also shield nearby gas clouds from the worst of the black hole's heat. By acting like cosmic insulation, magnetic fields might allow certain regions to stay cool enough for molecules to form and stars to ignite. It's a delicate dance. Too much turbulence destroys star-forming clouds, but just the right amount of pressure and protection can kickstart the process. What's truly fascinating is how this mirrors conditions in the early universe. Back then, galaxies were smaller and mergers more frequent, with black holes and star formation often coexisting in a violent tango. Centaurus A gives us a nearby lab to study how these processes might have shaped the first galaxies. Its star-forming pockets are a reminder that even in the most hostile environments, nature finds a way, sometimes with a little unintended help from the chaos itself. So, the next time you hear about a galaxy's violent core, remember, destruction and creation often go hand in hand. Centaurus A's star-forming paradox isn't just a curiosity, it's a clue to how galaxies evolve, survive, and even thrive amid the chaos. And as we'll see next, this galaxy has even more surprises tucked away in its swirling depths. Now, let's turn our attention to something truly unusual, a cosmic structure so rare that only a handful of galaxies are known to possess it. Centaurus A might just be hiding a polar ring, a dazzling loop of gas and stars orbiting perpendicular to the galaxy's main disk. If confirmed, this would be one of the most striking clues yet about its violent past. Polar rings are like celestial hula hoops wrapping around a galaxy's poles instead of aligning with its equator. They're thought to form when two galaxies collide and one gets torn apart, leaving its debris swirling at a right angle to the survivor's disk. For Centaurus A, this would fit perfectly with its reputation as a galactic cannibal. But here's the twist: not all astronomers agree the ring exists. Some observations suggest a faint, warped disk of gas and stars that could be a polar ring, while others argue it's just a trick of perspective with dust lanes and merger remnants masquerading as a ring. The debate hinges on two key pieces of evidence. First, there's the gas. Radio telescopes have detected hydrogen clouds moving in a way that doesn't match the galaxy's main disk. Their orbits seem tilted, as if tracing a separate structure. Second, infrared images reveal a faint smattering of stars following a similar path. Together, these hints paint a tantalizing picture, but critics point out that Centaurus A's messy interior, crisscrossed by dust lanes and still settling from past mergers, could easily mimic a polar ring without one actually being there. Then there's the question of stability. Polar rings are fragile. Over time, gravity should pull them back into alignment with the main galaxy, yet a few, like the famous polar ring galaxy NGC 4650A, have kept their rings for billions of years. Could Centaurus A's black hole, with its ferocious jets, be disrupting the ring's structure, making it harder to spot? Or does the ring's apparent faintness mean it's already dissolving, a fleeting relic of a long-ago collision? The implications are huge. If the ring is real, it would lock in Centaurus A's status as a merger addict, with the polar structure marking one of its most dramatic meals. It would also challenge our models of how such rings survive in galaxies with violent cores. But if it's an illusion, that raises another mystery. What then is causing the gas and stars to move so strangely? For now, the truth remains just out of reach, hidden behind Centaurus A's dusty veil. But with next-generation telescopes set to peer deeper into its chaos, we might soon have an answer. Either way, this debate reminds us that even the weirdest cosmic oddities are pieces of a larger puzzle, one that's still being assembled, one observation at a time. Now, shifting our gaze to another cosmic mystery lurking in Centaurus A, we encounter something that defies simple explanation: enormous clouds of hydrogen gas hurtling through space at speeds that leave astronomers scratching their heads. These aren't your average interstellar gas clouds. They move too fast in the wrong directions, almost as if something invisible is flinging them across the galaxy like cosmic projectiles. So what's going on? The leading theories point to two dramatic possibilities. First, these clouds could be the shattered remains of smaller galaxies torn apart during past mergers. As Centaurus A devoured its neighbors, their gas might have been scattered, sent careening at odd angles by the chaos of gravity. It's like throwing a glass of water into a fan. Some droplets go wild, defying expectations. The second, even more thrilling idea: the supermassive black hole at the galaxy's heart could be directly launching these clouds outward, its immense energy accelerating gas to unbelievable speeds. Evidence for both scenarios exists. Radio observations reveal hydrogen clouds moving at hundreds of kilometers per second, far faster than the galaxy's rotation should allow. Some even seem to be racing against the galaxy's natural motion, like cars speeding the wrong way down a highway. That's hard to explain without something violent disturbing them. The black hole's jets are a prime suspect, but not the only one. Simulations of galactic collisions show that mergers can leave behind rogue gas clouds with similarly bizarre trajectories. Here's where it gets even stranger. Some of these clouds aren't just moving fast, they're cold. Normally, gas accelerated by a black hole's fury would heat up dramatically, glowing in X-rays. But these clouds remain oddly chilly, suggesting they might be shielded by magnetic fields or compressed in ways we don't yet understand. Others show signs of recent star formation, meaning they've lingered long enough for gravity to collapse pockets of gas into new stars, something that shouldn't happen if they were just ejected by the black hole. The debate isn't just academic. If the black hole is launching these clouds, it would mean its influence stretches even farther than we thought, reshaping gas across vast distances. If mergers are the culprit, it would highlight how the wreckage of past collisions lingers for eons, subtly shaping the galaxy's evolution. There's also a wild card: dark matter. Could invisible halos around Centaurus A be tugging on these clouds, adding to their erratic motion? For now, these runaway gas clouds remain one of Centaurus A's most puzzling riddles. Every new observation adds another layer. Some clouds seem to align with the black hole's jets, others sprawl in directions that defy easy explanation. It's a reminder that in a galaxy this chaotic, even something as simple as a gas cloud can hold secrets that challenge our understanding of physics itself. Now, as we peel back another layer of Centaurus A's mysteries, we stumble upon a curious absence: globular clusters. Those dense, ancient swarms of stars that typically orbit galaxies like bees around a hive are strangely scarce here. Most galaxies of its size, like our Milky Way, boast hundreds of these glittering relics from the early universe. Yet Centaurus appears to have far fewer, and astronomers are piecing together why this cosmic antique shop might be missing so many treasures. The leading suspicion: Centaurus A's violent past. Picture this: globular clusters are tough but not indestructible. They form in the calm outskirts of galaxies where gravity's grip is gentle. But Centaurus A is anything but calm. Its history of galactic collisions devouring smaller galaxies like a cosmic predator likely ripped apart many of these clusters. When galaxies merge, their gravitational dance can fling clusters into intergalactic space or tear them apart entirely, scattering their stars into the galaxy's halo like sand in a storm. Some clusters might have even plunged too close to the supermassive black hole, where tidal forces shredded them into stellar streams. There's another twist. The clusters that do survive in Centaurus are oddballs. Some glow unusually red, hinting at chemical compositions altered by the galaxy's turbulent environment. In quieter galaxies, globular clusters are pristine time capsules. They're stars forged in the early universe with minimal pollution from later generations. But here, the chaos of mergers may have heated gas, triggering new star formation within the clusters and polluting their original chemistry. It's like finding a centuries-old manuscript with modern ink smudged across its pages, still valuable but with a story muddled by interference. The mystery deepens when we compare Centaurus A to its galactic neighbors. Take NGC 5128, a similar massive galaxy, which has a rich system of globular clusters. Why the difference? One theory suggests Centaurus A's black hole played a role. Its intense jets and outbursts could have sterilized the surrounding regions, preventing new clusters from forming or vaporizing existing ones. Alternatively, the galaxy's dark matter halo. Its invisible gravitational scaffold might be structured differently, offering fewer safe havens for clusters to survive. But here's the real puzzle. If mergers destroyed so many clusters, where are the leftover stars? Astronomers hunt for faint streams of stars in Centaurus A's halo, the expected debris from shredded clusters. Some have been found, but not enough to account for the missing thousands. Could they be hiding in the galaxy's thick dust lanes, or were they assimilated so thoroughly that they're now indistinguishable from the rest of the stellar population? The absence of globular clusters isn't just a curiosity, it's a clue. These missing relics could reveal how often Centaurus A has collided with other galaxies, how violently its black hole has erupted, and even how dark matter is distributed around it. Every undetected cluster is a silent witness to the galaxy's roughest moments, and their ghosts may yet guide us to a deeper understanding of this cosmic enigma. Shifting our gaze to another intriguing puzzle, let's explore why Centaurus A blazes so brilliantly in infrared light. While this galaxy might appear chaotic and dusty in visible light, when viewed through infrared telescopes, it becomes a radiant beacon, revealing secrets hidden from other wavelengths. This unusual brightness isn't just a curiosity, it's a window into the galaxy's hidden activity. The first clue lies in Centaurus A's thick dust lanes, which crisscross its core like cosmic cobwebs. These lanes, laced with tiny particles of carbon and silicon, absorb visible light, making parts of the galaxy seem dark or obscured. But when the same dust absorbs energy, whether from starlight or the supermassive black hole's fury, it heats up and re-emits that energy as infrared radiation. Think of it like holding your hand near a hot stove. You can't see the heat, but you feel it. In Centaurus A, the dust acts similarly, glowing brightly in infrared as it soaks up energy from its violent surroundings. The supermassive black hole plays a starring role here. Its jets and accretion disk pump out immense amounts of energy, much of which gets absorbed by the surrounding dust. This process turns the galaxy's core into an infrared furnace, with temperatures soaring high enough to make the dust glow intensely. But it's not just the black hole's immediate neighborhood that lights up. The galaxy's turbulent mergers have scattered dust far and wide, meaning even regions distant from the core can heat up and contribute to the infrared glow. But there's another twist. Buried within those dusty veins are hidden stellar nurseries, regions where new stars are forming at a surprising rate. Normally, thick dust would block our view of these nurseries in visible light, but infrared pierces through, exposing the vibrant star-forming activity beneath. This hidden star birth adds to the galaxy's infrared brilliance, as young, massive stars heat their surrounding dust clouds, making them shine even brighter. It's like discovering a bustling city hidden beneath a dense fog. Only infrared vision can reveal its true scale. What makes Centaurus A stand out, though, is how its infrared emissions defy expectations. Compared to other galaxies with similar black hole activity, Centaurus A's infrared output is unusually high. Some astronomers speculate this could be due to its unique merger history, which may have funneled extra gas and dust into the galaxy, providing more material to heat up. Others suggest its black hole's jets might be interacting with the dust in unconventional ways, creating hotspots that outshine predictions. This infrared brightness isn't just a spectacle, it's a vital clue. By studying it, astronomers can map where dust is concentrated, track how energy flows through the galaxy, and even estimate how much star formation is happening behind the veil. It's a reminder that sometimes the most revealing light is the one we can't see with our eyes alone. And as we'll soon discover, Centaurus A has even more surprises waiting just beyond the infrared glow. Now let's unravel another cosmic oddity that makes Centaurus A so peculiar: the mysterious case of its counter-rotating gas disks. Picture this. Most galaxies rotate like a giant spinning top, with stars, gas, and dust all moving in harmony. But Centaurus A breaks the rules. Deep within its core, astronomers have discovered something bizarre: an inner disk of gas swirling in the exact opposite direction of the stars around it. It's as if part of the galaxy decided to dance to its own rhythm, defying the cosmic norm. What could cause such a strange twist? The leading theory points to a dramatic galactic collision in Centaurus A's past. Imagine two galaxies merging, each with its own rotation. If one was spinning clockwise and the other counterclockwise before they collided, the gas from the smaller intruder could have been dragged into the larger galaxy's core, preserving its original spin direction. Over time, this misbehaving gas settled into a disk that now rotates backward compared to the rest of the galaxy, a fossilized record of that ancient cosmic crash. This counter-rotation isn't just a curiosity, it's a forensic clue. By studying the speed and tilt of these opposing disks, astronomers can reconstruct the angle and violence of the collision that created them. Some models suggest the merger happened nearly a billion years ago, with the smaller galaxy coming in at a steep, almost perpendicular angle. The gravitational tug of war that followed would have twisted and warped both galaxies, leaving behind the chaotic structure we see today. Here's where it gets even weirder. Counter-rotating gas isn't just spinning backward, it's also feeding the supermassive black hole in unexpected ways. As the gas moves against the flow of surrounding material, it creates violent turbulence, smashing into other gas clouds and triggering shock waves. These collisions can funnel material toward the black hole at unusual angles, possibly explaining why its jets spew out in such chaotic directions. It's like throwing a log into a river flowing the opposite way. The resulting splash goes everywhere, but the mystery deepens when we consider how rare this phenomenon is. While a handful of galaxies show hints of counter-rotation, Centaurus A's case is extreme, with its inner gas disk spinning nearly perfectly opposite to its stars. Some researchers speculate this might mean the galaxy has cannibalized more than one smaller neighbor, with each merger adding another layer of chaos. Others wonder if dark matter played a role, its invisible gravitational influence twisting the gas into this strange configuration. For astronomers, these counter-rotating disks are more than just a puzzle, they're a living laboratory. By watching how gas and stars interact in such an unbalanced system, they can test theories about how galaxies evolve after mergers. Every new observation peels back another layer, revealing how violence and chaos can shape a galaxy's destiny. And as we'll see next, Centaurus A's surprises don't stop there. Its turbulent past has left even more bizarre fingerprints across the cosmos. Now let's shift our focus to another head-scratching mystery lurking within Centaurus A, ultra-luminous X-ray sources, or ULXs for short. These cosmic powerhouses are like the overachievers of the X-ray universe, blasting out energy at levels that defy expectations. A typical neutron star, for instance, might shine brightly in X-rays, but ULXs crank that brightness up by hundreds or even thousands of times. Imagine a flashlight suddenly outshining a stadium spotlight. That's the kind of extreme we're dealing with here. So what could possibly produce such staggering energy? Astronomers have two leading theories. The first suggests these ULXs might be intermediate mass black holes, bridging the gap between the smaller stellar mass black holes and the supermassive behemoths at galactic centers. These middleweights would pack the mass of hundreds or even thousands of suns into a single point, devouring surrounding material so ferociously that they glow incredibly bright in X-rays. If confirmed, they'd solve a long-standing puzzle in astrophysics: how supermassive black holes grow so enormous. But there's another intriguing possibility: exotic binary systems. Picture a neutron star or a regular stellar mass black hole locked in a tight orbit with a massive companion star. If the star pours material onto its dense neighbor at an unusually high rate, the resulting X-ray emission could get a dramatic boost. Some models even suggest magnetic fields or beamed radiation might act like cosmic amplifiers, making these systems appear far brighter than they actually are. It's like holding a magnifying glass over a light bulb. The light isn't stronger, but it looks that way from our vantage point. Centaurus A adds even more layers to the intrigue. Unlike many galaxies where ULXs are rare, this one hosts several, scattered across its chaotic landscape. Their locations tell a story. Some nestle in young star clusters, hinting at recent stellar fireworks, while others lurk near regions scarred by past mergers. This distribution suggests ULXs might thrive in environments where violence and upheaval are common, as if the galaxy's turbulent history provided the perfect breeding ground for these extreme objects. The debate over their true nature isn't just academic. If ULXs are intermediate black holes, they'd reshape our understanding of how black holes form and grow. If they're exotic binaries, they'd reveal new extremes of stellar behavior, and Centaurus A, with its unique mix of galaxies, offers a front-row seat to this cosmic detective story. As telescopes grow sharper, each new observation brings us closer to cracking the case, one dazzling X-ray flash at a time. Just when we thought Centaurus A couldn't get any stranger, there's another twist: its gamma-ray emissions have a mind of their own. Unlike the steady glow of most galaxies, this one flickers unpredictably, as if something deep inside is switching on and off at random. Gamma rays are the universe's most energetic light, packing a punch millions of times stronger than visible light, so when their levels dance around like this, it demands an explanation. One leading theory points to the supermassive black hole's appetite. Think of it like a cosmic furnace. Sometimes it's feasting on gas and dust, other times it's between meals. During feeding frenzies, the black hole's disk gets hotter and more turbulent, potentially accelerating particles to extreme speeds and producing gamma-ray flares. But when the flow of material slows, the gamma-ray output might dip. It's akin to a bonfire roaring one moment and smoldering the next, depending on how much fuel you toss in. Then there's the jet instability angle. Centaurus A's colossal jets aren't just steady streams, they're chaotic, with knots and shocks that could trigger sudden gamma-ray bursts. Magnetic fields within the jets might snap and reconnect, releasing energy in violent spikes, much like a solar flare but on a galactic scale. These instabilities could explain why the gamma rays don't follow a neat pattern, instead flaring up in fits and starts. What makes this variability especially puzzling is how it defies models. Simulations predict smoother changes, yet Centaurus A's gamma rays jump around as if something's interrupting the process. Could there be unseen structures in the jets, like hidden clumps of denser material? Or is the black hole's disk warped, causing uneven feeding? Each observation adds another piece to the puzzle. One thing's clear: this isn't just about Centaurus A. Understanding these fluctuations could shed light on how black holes across the universe influence their surroundings. If feeding cycles drive the changes, it might reveal how black holes grow over time. If jet instabilities are to blame, it could rewrite how we think about these high-speed particle accelerators. For now, the galaxy keeps its secrets, but with every flicker it offers clues. One day, those clues might just unravel the mystery. Now, let's peel back another layer of Centaurus A's strangeness: its magnetic fields. This galaxy doesn't just have magnetic fields, it has cosmic spaghetti bowls of them, twisted and tangled in ways that baffle scientists. Radio telescopes have mapped these fields near the jets, revealing knots and loops that look more like an abstract painting than the orderly lines we'd expect. So, why does this matter? Magnetic fields are like invisible puppet masters for Centaurus A's jets. They guide and shape those high-speed particle streams, determining how far they stretch and where their energy goes. Without these fields, the jets would likely spray out in all directions, like a garden hose with no nozzle. But here, the fields are so contorted that they create chaos. Some particles get funneled into tight beams, while others spiral wildly, creating those shimmering radio lobes we see millions of light-years away. The twists themselves might come from the black hole's brutal environment. Picture this: gas and dust swirl into the black hole at nearly light speed, dragging magnetic field lines along like taffy. Those lines stretch, snap, and reconnect, releasing bursts of energy. Sometimes they even double back on themselves, creating loops that trap particles and heat them to extreme temperatures. It's like a cosmic version of a knotted shoelace, except this lace is made of pure magnetism and packs enough power to light up galaxies. What's even wilder is how these fields might explain some of Centaurus A's other oddities. Those unpredictable gamma-ray flares we just talked about, the twisted magnetic fields could be part of the reason. When the fields reconfigure suddenly, they might launch particles to near light speed in an instant, producing those high-energy flashes. And those knotty structures in the X-ray jets, they could be tied to spots where the magnetic fields are especially tangled, like traffic jams in a particle freeway. But here's the catch: we still don't know exactly how these fields get so warped. Some theories suggest past mergers twisted them like a pretzel. Others point to turbulence in the black hole's disk, where magnetic lines get caught in whirlpools of infalling material. Every new radio map adds more questions, revealing patterns that don't match our simulations. One thing's certain: these magnetic fields are more than just background noise. They're key players in the galaxy's drama, shaping everything from the jets to the gamma rays. And if we can decode their secrets, we might finally understand how black holes sculpt their cosmic neighborhoods. For now, though, Centaurus A keeps its magnetic mysteries tightly wound. Moving deeper into the mysteries of Centaurus A, we now turn our attention to its haunting outer edges. Wrapped around this galaxy like cosmic whispers are faint, arc-shaped formations known as shell structures. These aren't just random scatterings of stars, they're the ghostly fingerprints of past galactic collisions, telling a story of violence and rebirth. These shells are made up of stars that were once part of smaller galaxies torn apart by Centaurus A's immense gravity. Imagine throwing a pebble into a pond, the ripples spread outward, right? Now picture that same effect, but on a galactic scale. When a smaller galaxy gets too close, Centaurus A's gravity shreds it apart, flinging stars into long, looping arcs that settle into these eerie shells. Over time, they fade into the darkness, leaving behind these faint, ethereal traces. What makes these shells so fascinating is how they reveal the galaxy's brutal history. Each one is like a layer in an archaeological dig, marking a different merger event. Astronomers have counted multiple shells around Centaurus A, meaning this galaxy has been feasting on its neighbors for billions of years. The outermost shells are the oldest, the remnants of ancient cosmic meals, while the inner ones might be from more recent galactic snacks. But here's where it gets even stranger. These shells shouldn't be as smooth or symmetrical as they appear. Normally, when a galaxy gets ripped apart, its stars should scatter chaotically. Yet in Centaurus A, they've settled into these neat, curved patterns. One leading theory suggests that dark matter is pulling the strings here. Its invisible gravitational grip might be organizing the debris into these orderly shells. Another idea points to the supermassive black hole's influence, its powerful gravity acting like a cosmic blender, smoothing out the chaos over time. These ghostly structures also give us clues about the galaxy's future. With every merger, Centaurus A grows larger and more turbulent. Eventually, those shells will dissolve completely, their stars absorbed into the galaxy's main body. But for now, they linger as silent witnesses to the galaxy's violent past, a past that's still shaping its present. So next time you look at an image of Centaurus A, don't just focus on its bright core or dramatic jets. Take a moment to search for those faint, glowing arcs at its edges. They're not just debris, they're the echoes of cosmic battles fought long ago, battles that helped forge one of the most peculiar galaxies in our universe. Now, let's pull back the curtain on another intriguing puzzle hiding in Centaurus A's shadowy outskirts. Astronomers have long noticed something odd about the way stars move in this galaxy. Some seem to wobble or drift in ways that don't quite match expectations. One compelling explanation: an unseen companion, a dwarf galaxy lurking just out of sight, its presence betrayed only by the subtle tugs it exerts on its colossal neighbor. This hidden dwarf, if it exists, would likely be veiled behind Centaurus A's thick dust lanes or drowned out by its dazzling core, but gravity doesn't lie. The odd motions of stars and gas clouds near the galaxy's outer edges suggest an invisible dance partner, a small but massive object orbiting Centaurus A, its gravitational pull warping the paths of nearby stars like a hidden magnet bending iron filings. Dwarf galaxies are common satellites of larger galaxies. Our own Milky Way has dozens, but finding one around Centaurus A is tricky. Unlike the Milky Way's companions, which are relatively clean and easy to spot, Centaurus A's potential dwarf would be shrouded in dust or fragmented from past encounters, making it a ghost in the data. Some researchers argue that strange stellar streams or clumps of stars in the galaxy's halo could be the shredded remains of this elusive companion, torn apart by tidal forces but still influencing the system. There's another twist. If this dwarf galaxy is particularly rich in dark matter, as many small galaxies are, its gravitational fingerprint would be even stronger. Dark matter doesn't interact with light, so it could be pulling on Centaurus A's stars without leaving a visible trace. Computer simulations show that such a hidden companion could explain why some stars in Centaurus A's outskirts move faster than expected, as if tugged by an unseen hand. But the mystery deepens when we consider alternative explanations. Could these odd motions come from Centaurus A's own turbulent history, mergers stirring up chaos, or jets from the black hole pushing gas around? It's possible, yet the patterns match what we'd expect from a small, dense object orbiting nearby. The hunt for this phantom galaxy is ongoing, with telescopes probing the dust-choked regions around Centaurus A for any faint glow or clustered stars that might give it away. If confirmed, this unseen companion would add another layer to Centaurus A's already dramatic story. It's a reminder that even in the brightest galaxies, the darkest corners might still hide secrets, waiting for the right tools or the right moment to reveal themselves. But the surprises in Centaurus A don't stop there. Let's turn our attention to something even more exhilarating: stars that seem to defy the galaxy's gravitational rules. Scattered across Centaurus A are stellar speedsters, stars hurtling through space at velocities so extreme they should have escaped the galaxy altogether. Yet somehow they remain bound to this cosmic juggernaut, racing through its outskirts like celestial outlaws. These high-velocity stars present a fascinating puzzle. Normally, stars move in predictable orbits dictated by their galaxy's gravity. But in Centaurus A, some stars appear to be moving nearly twice as fast as expected, with trajectories that don't match the typical flow of stellar traffic. One leading theory: they might be the survivors of a cosmic slingshot flung outward by the galaxy's supermassive black hole. Imagine a binary star system, two stars orbiting each other, drifting too close to the black hole's gravitational grip. If one star gets captured, the other can be ejected at extraordinary speeds like a gravitational slingshot effect. This could explain why some stars in Centaurus are zipping through space as if they've been fired from a cannon. Computer simulations show these kinds of interactions are possible, and Centaurus A's violent core makes it a prime suspect for such stellar catapults. But the black hole isn't the only possible culprit. Another explanation points to the galaxy's turbulent merger history. When galaxies collide, gravitational chaos can send stars careening in all directions. Some might get hurled out entirely, becoming rogue stars drifting through intergalactic space. Others, like those we see in Centaurus A, might just barely stay bound to the galaxy, zooming through on extreme trajectories. There's an even wilder possibility. Some of these stars might not be native to Centaurus A at all. If a smaller galaxy passed too close and was torn apart, its stars could have been scattered at high speeds, now orbiting in unexpected patterns. This could explain why some high-velocity stars appear in clusters, remnants of their original home, now strewn across their new, chaotic environment. Tracking these stars is no easy task. Many are faint, lost in the galaxy's glare or hidden behind dust lanes. But with advanced telescopes and careful spectral analysis, astronomers have begun mapping their paths. Some even show chemical signatures suggesting they were born in a different environment, further supporting the idea that they're intergalactic intruders. What's truly mind-boggling is that some of these speedster stars might hold clues about the galaxy's deepest secrets. Their trajectories could reveal the distribution of dark matter, the strength of the black hole's past eruptions, or even the timing of ancient collisions. If we follow their lead, they might just guide us to the next great discovery in Centaurus A's ever-unfolding mystery. Now, let's step into the realm of cosmic echoes where the past whispers to us across the void. Deep within Centaurus A, astronomers suspect the galaxy's supermassive black hole hasn't always been as quiet as it seems today. Centuries or even millennia ago, it might have unleashed monstrous eruptions, blasting energy into space. And while those events have long since faded, their ghostly fingerprints could still linger as faint light echoes, scattered reflections of those ancient outbursts, bouncing off dust and gas like ripples in a cosmic pond. These echoes are incredibly elusive. Imagine a flashlight beam hitting a wall in a pitch-black room. The initial flash is gone, but for a split second, the light lingers as a faint glow. In space, that glow can travel for centuries, bouncing off interstellar dust before eventually reaching us. For Centaurus A, detecting these echoes would be like uncovering a hidden chapter in the galaxy's violent history. Astronomers hunt for them by comparing old and new images, searching for subtle brightening in dust clouds that shouldn't otherwise change the challenge. These echoes are staggeringly faint, buried in the galaxy's already chaotic light. To spot them, scientists use specialized filters and painstakingly analyze wavelengths where dust scattering is most visible, like infrared and X-rays. Sometimes the echoes manifest as delicate rings or arcs of light, expanding outward from the black hole at the speed of light, visual records of eruptions that occurred hundreds of years ago. In other galaxies, like our own Milky Way, similar echoes have been found, revealing past outbursts we'd otherwise never know about. What makes Centaurus A particularly intriguing is its dust-rich environment. Those iconic warped dust lanes we discussed earlier, they're not just obscuring the galaxy's core, they're also potential screens for light echoes. If the black hole erupted in the past, its energy would have illuminated these dust structures, creating reflections that might still be drifting toward us. Catching them would confirm that Centaurus A's black hole has a history of violent mood swings, alternating between dormancy and cataclysmic activity. But why does this matter? Light echoes aren't just cosmic trivia, they're time capsules. By measuring their expansion and brightness, astronomers can estimate when the original eruption happened and how much energy it released. This could reshape our understanding of how often supermassive black holes wake up and how their outbursts influence galaxy evolution. If Centaurus A's echoes are found, they might even hint at whether its current jets are part of a recurring cycle, building toward another eruption in the distant future. The search isn't easy. It requires cutting-edge telescopes with unmatched sensitivity, plus a bit of luck. But if astronomers succeed, these faint reflections could reveal secrets about the black hole's behavior that no other method can uncover. After all, in a galaxy as enigmatic as Centaurus A, even the faintest whispers from the past might hold the loudest answers. Shifting our focus from the echoes of violent outbursts, let's zoom in on something far smaller yet equally fascinating: the intricate chemistry brewing within Centaurus A's twisted dust lanes. These dark, chaotic ribbons aren't just cosmic roadblocks obscuring our view. They're bustling laboratories where molecules, some incredibly rare, come together under conditions unlike anywhere else in the galaxy. At first glance, dust lanes might seem simple, just clouds of soot and gas, but probe deeper and you'll find a molecular menagerie. Beyond common compounds like carbon monoxide or water ice, astronomers have spotted hints of exotic molecules, including polycyclic aromatic hydrocarbons. These are essentially tiny, carbon-based structures that resemble fragments of soot or even the building blocks of life. In Centaurus A's dust lanes, they form in the turbulent wake of the galaxy's violent history, where shockwaves from mergers and black hole activity compress and heat gas to extremes. What makes this especially intriguing is how these molecules behave under such chaos. Normally, harsh radiation from stars or black holes would tear molecules apart. Yet here they persist, One theory suggests the dust lanes act like cosmic shields, their dense layers absorbing destructive energy while sheltered pockets allow chemistry to thrive. It's like a bustling marketplace in the middle of a hurricane. Somehow, business carries on. Then there's the mystery of formaldehyde and methanol detected in surprising quantities. On Earth, these are used in industrial processes. Even formaldehyde's a preservative. In space, their presence hints at chemical pathways we're still unraveling. Some researchers propose they form on the icy surfaces of dust grains, where atoms meet and react in the cold void. Others speculate Centaurus A's turbulent environment accelerates these reactions like a pressure cooker for interstellar molecules. The implications stretch far beyond this single galaxy. If complex molecules can form and survive here, it challenges our assumptions about where and how chemistry unfolds in the universe. Typically, we associate molecule-rich environments with calmer, star-forming regions. But Centaurus A flips that script, proving even chaos can be a cradle for complexity. This molecular puzzle also ties into the bigger picture of galactic evolution. Every time Centaurus A devours a smaller galaxy or unleashes a jet from its black hole, it injects energy and raw materials into these dust lanes, potentially sparking new rounds of chemical experimentation. Over billions of years, these processes could seed the galaxy with organic compounds, some of which might even find their way into future generations of stars and planets. The search for these molecules isn't just academic. It's a step toward answering whether the ingredients for life are rare or universal. If harsh environments like Centaurus A can brew complex chemistry, maybe life's building blocks are more resilient and widespread than we ever imagined. Next time you see an image of those dark, swirling dust lanes, remember, they're not just shadows. They're some of the universe's most dynamic kitchens, cooking up mysteries one molecule at a time. Now, let's turn our attention to another head-scratching quirk of Centaurus A, the strange, wobbly dance of its jets. Normally, the colossal beams of energy shooting from a supermassive black hole's poles are laser-straight, piercing the cosmos like cosmic searchlights. But not here. In Centaurus A, these jets seem to sway over time as if pushed by an invisible hand. Astronomers call this jet precession, and it's one of the most puzzling behaviors we've observed in this galaxy. So what's causing it? One leading theory points to a warped accretion disk. Picture the disk of gas and dust spiraling into the black hole like water circling a drain. If that disk isn't perfectly flat, if it's bent or twisted, it could drag the jets along with it, forcing them to wobble as they shoot outward. Think of it like a spinning top that's slightly off balance. The tilt makes it wobble as it rotates. In Centaurus A, gravitational forces from past galactic collisions or uneven gas inflows might have warped the disk, creating this unstable spin. But there's another, even wilder possibility: a second black hole. Some astronomers speculate that Centaurus A's supermassive black hole might have a smaller companion, locked in a gravitational tango. As the two orbit each other, their combined pull could yank the primary black hole's jets back and forth, like a garden hose thrashing under high pressure. Binary black holes are rare, but they're not unheard of, especially in galaxies with a violent merger history like Centaurus A. If true, this would make the galaxy's core a cosmic wrestling match with jets caught in the crossfire. The evidence for either scenario is still murky. Radio telescopes have tracked the jet's swaying motion, but pinpointing the exact cause requires sharper observations. Some studies suggest the wobble follows a predictable pattern, which leans toward the warped disk idea. Others note abrupt changes in the jet's direction, which could hint at the gravitational nudges of a hidden companion. What's at stake isn't just solving a local mystery. Jet precession affects how energy spreads through the galaxy. These jets' heat surrounding gas suppress star formation and even shape Centaurus A's iconic radio lobes. If they're wobbling, that energy isn't being distributed evenly. some regions get blasted more than others, potentially altering the galaxy's evolution. And there's a bigger picture here too. If a binary black hole is the culprit, it raises tantalizing questions. How often do supermassive black holes pair up? Do they eventually collide, sending ripples through space-time? Centaurus A's wobbly jets might be giving us a front-row seat to a slow-motion cosmic merger, one that could end with a gravitational wave crescendo billions of years from now. For now, the mystery endures, but every flicker in those jets is a clue, a breadcrumb leading us closer to understanding the dynamic chaos at the heart of Centaurus A. One thing's certain, this galaxy never stops surprising us. Shifting our focus from the wobbly jets, we encounter another cosmic puzzle in Centaurus A. Where are all the supernova remnants? In a galaxy this active, with pockets of vigorous star formation, you'd expect to find the ghostly afterglow of exploded stars scattered everywhere. Yet, strangely, astronomers have spotted far fewer supernova remnants than predicted. It's like throwing a party and realizing half the guests never showed up. So what's going on here? One explanation could be Centaurus A's infamous dust lanes. Those thick, twisting ribbons of cosmic grit, remnants of past collisions, might be playing hide and seek with our telescopes. When a massive star explodes as a supernova, it leaves behind a glowing shell of gas and debris, often visible in radio or X-ray wavelengths. But if these remnants are buried deep behind dense dust clouds, their light could be absorbed or scattered, rendering them nearly invisible to our instruments. Imagine trying to spot a flashlight beam through a snowstorm. That's the challenge astronomers face. Then there's the possibility that supernova in Centaurus are simply rarer than we'd expect. Star formation here is patchy, confined to specific regions rather than evenly spread. If most massive stars are born in these pockets, their explosions might be clustered too, leaving vast, dead zones without remnants. Alternatively, the galaxy's turbulent environment, shaped by its supermassive black hole, could disrupt the usual life cycle of stars. Intense radiation and magnetic fields might prevent some massive stars from forming altogether, or even alter how they die. For instance, a star might collapse directly into a black hole without a dramatic supernova, leaving no remnant behind. But here's where it gets even weirder. Some studies suggest the remnants we do see in Centaurus look different from those in common galaxies. They're often fainter or more fragmented, as if the galaxy's chaotic core has torn them apart. The jets and outflows from the black hole could be shredding these gaseous relics, dispersing them before they fully develop. It's like trying to preserve a sandcastle in a hurricane. The conditions are just too extreme. The implications stretch beyond Centaurus A. Supernova remnants are cosmic recyclers, injecting heavy elements back into space to form new stars and planets. If they're missing or stunted here, it could skew the galaxy's chemical evolution. Less recycled material might mean fewer rocky planets or even alter the types of stars that can form in the future. So is the dust hiding them, or is Centaurus somehow breaking the rules? The answer might lie in next-generation telescopes, like the James Webb Space Telescope, which can peer through dust with its infrared eyes. Or perhaps upcoming radio arrays will catch whispers of remnants we've overlooked. For now, this absence remains a quiet enigma, a reminder that even in the busiest galaxies, the universe still keeps a few secrets close. As we piece together these clues, we're not just solving a local mystery. We're learning how extreme environments shape the life and death of stars, and what that means for galaxies across the cosmos. Now, let's turn our attention to a splash of unexpected color in Centaurus A's stellar tapestry. Among the galaxy's ancient globular clusters, tightly bound groups of stars that date back billions of years, astronomers have spotted something peculiar. While most of these clusters shine with the familiar golden hue of aging stars, a handful blaze with an unusually deep red tint. This isn't just a cosmic quirk of lighting. That crimson glow is a fingerprint telling the story of a violent past written in starlight. Globular clusters are meant to be time capsules, preserving the chemical makeup of the early universe. Normally, their stars are poor in heavy elements like iron, having formed before generations of supernova enriched the cosmos, but these red outliers break the mold. Their color suggests they're packed with more metals than expected, as if someone sprinkled extra ingredients into their stellar recipe. So where did these metallic stars come from? The leading theory points straight to Centaurus A's history of galactic collisions. Imagine two galaxies merging like swirling cups of coffee. Their stars don't just pass through each other but drag along clouds of gas rich in heavy elements. When such mergers trigger new star formation within globular clusters, the newborn stars inherit this chemical pollution. The result, a cluster that's visibly redder than its pristine neighbors. Some of Centaurus A's red clusters might even be stolen relics, cannibalized from smaller galaxies that got too close. Their unusual chemistry would then be a souvenir from their original home. But the plot thickens. These red clusters aren't just chemically odd, they're also younger than the galaxy's typical globulars. While most formed over 12 billion years ago, the red interlopers might be as youthful as 8 billion years, coinciding with when Centaurus A began its merger spree. It's as if the galaxy's violent reshuffling gave birth to a second generation of clusters, each one a time-stamped record of past collisions. What makes this discovery so valuable is that it turns these clusters into cosmic archaeologists. By studying their redness, their motion, and their ages, astronomers can reconstruct the sequence of mergers that built Centaurus A. Some clusters might trace back to a single, dramatic collision, while others could be remnants of multiple smaller snacks. Even their orbits hold clues. Those flung into wide, looping paths likely arrived during violent encounters, while tighter orbits suggest a more peaceful adoption. This isn't just about coloring in Centaurus A's family album. Globular clusters influence their host galaxy's evolution, seeding it with stars and shaping its gravitational field. If a significant fraction are red metal-rich newcomers, they could have altered how Centaurus A's stars and gas are distributed today. Future telescopes like the Extremely Large Telescope might even spot individual stars being stripped from these clusters, leaving crimson trails across the galaxy, a direct glimpse of mergers in action. So the next time you see an image of Centaurus A, remember, those faint red dots aren't just decorative. They're the surviving witnesses to a history of galactic cannibalism, each one whispering secrets about how the universe builds its giants. And as we decode their stories, we're not just learning about one peculiar galaxy. We're uncovering the universal recipe for turning cosmic chaos into celestial order. Shifting our gaze to another cosmic puzzle, let's examine a curious case of missing light in Centaurus A. For years, astronomers have noticed something odd when they point ultraviolet telescopes toward this galaxy. It emits far less ultraviolet light, the high-energy radiation typically linked to young, hot stars, than models predict. It's as if someone dimmed a cosmic flashlight, leaving scientists to wonder whether the issue lies with obscured starlight or a fundamental misunderstanding of how stars form in this chaotic environment. To grasp why this deficit matters, picture the universe's light as a language. Far ultraviolet light acts like a specific dialect, one that only the hottest, most massive stars can speak. These stars burn bright and fast, living mere millions of years before exploding as supernova. Normally, galaxies with active star formation like Centaurus A's dusty pockets should glow intensely in this ultraviolet range. But here, the signal falls strangely short. One explanation points to the galaxy's infamous dust lanes. Just as fog scatters a car's headlights, dust grains could be absorbing or scattering far UV light before it escapes Centaurus A. This wouldn't be surprising given the galaxy's messy merger history, which likely left it shrouded in thick clouds of interstellar grit. Supporters of this theory note that infrared telescopes do detect heat from dust that's presumably warmed by trapped UV radiation. It's like finding warm footprints in snow, evidence that energy passed through, even if we didn't see the light itself. Yet not everyone is convinced dust tells the whole story. An alternative idea suggests Centaurus A might be forming stars in an unusual way. Perhaps mergers disrupted the typical recipe for star birth, leading to fewer massive stars than expected. Imagine baking a cake but swapping ingredients mid-recipe, you'd end up with a different result. Similarly, if collisions altered the distribution of gas clouds, the galaxy could produce more small, long-lived stars which emit little UV and fewer short-lived giants. This would explain the deficit without invoking dust at all. Intriguingly, both theories could be partly right. Observations show that Centaurus A's star-forming regions aren't evenly distributed. Some zones, like those near the warped dust lanes, might indeed hide UV light behind curtains of dust. Meanwhile, other areas could genuinely lack massive stars due to turbulent conditions from past mergers. The James Webb Space Telescope's sharp infrared vision may soon help settle the debate by peering through dust to census the galaxy's stellar population directly. This isn't just academic curiosity. Far UV light influences how galaxies evolve. It ionizes gas, drives winds, and even helps regulate future star formation. If Centaurus A's deficit stems from dust, it's a reminder of how messy cosmic visibility can be. But if the galaxy truly forms stars differently, it challenges our universal models of stellar birth. Either way, this missing light forces us to rethink how violence and chaos shape the lives of galaxies, and how much we still have left to learn. Turning our attention to another layer of intrigue, let's unravel the mystery of Centaurus A's ghostly radio filaments. Stretching like cosmic spiderwebs through the galaxy's colossal radio lobes, these wispy, thread-like structures defy easy explanation. Some appear no thicker than a few light years across, yet they span distances that dwarf entire star systems. Their delicate forms contrast sharply with the violent energy of the lobes they inhabit, leaving astronomers to wonder, are these filaments scars from ancient shock waves, or do they trace hidden magnetic skeletons shaping the galaxy's outbursts? To understand why these filaments puzzle scientists, picture the radio lobes as turbulent rivers of charged particles, spewed outward by the supermassive black hole's jets. Normally, such chaotic environments would smear out fine details like a storm erasing footprints in sand. Yet these filaments persist, their crisp edges suggesting something is either sculpting them or shielding them from disruption. One leading theory proposes they're fossilized shock waves, remnants of past jet surges that compressed and heated gas, leaving behind glowing trails. Imagine slapping the surface of a pond. The ripples freeze in time, preserving a moment of impact. Similarly, if the black hole's jet power fluctuated, each burst could have generated shock fronts that now linger as these eerie threads. But magnetism offers an equally compelling explanation. The filaments could be cosmic ropes woven from twisted magnetic field lines. In this scenario, the black hole's jets act like giant particle accelerators, tangling magnetic fields as they funnel material outward. Where these fields grow dense enough, they might trap and focus radio-emitting particles, creating the illusion of glowing threads. Think of it as squeezing toothpaste from a tube. The paste here, radio waves, follows the path of least resistance, highlighting the tube's shape. Supporting this idea, some filaments align neatly along the lobe's edges, much like iron filings tracing the outline of a bar magnet. The debate isn't just academic. If shock waves forged the filaments, they'd serve as timelines, chronicling the black hole's past eruptions. But if magnetism sculpted them, they'd reveal how energy channels through intergalactic space, a process key to understanding how galaxies influence their surroundings. Intriguingly, some filaments even appear to connect the lobes to the galaxy's core, like umbilical cords feeding energy outward. New radio telescopes like the Square Kilometre Array aim to map these structures in unprecedented detail, potentially settling their origin. What's clear is that these filaments aren't mere decoration. They're clues to the invisible forces, whether shock fronts or magnetic highways, that govern how Centaurus A interacts with the universe beyond its borders. And as we decode their messages, we edge closer to understanding how even the most delicate cosmic threads can hold galaxies together. Now, shifting our gaze to the heart of Centaurus A, we encounter a puzzle hidden in plain sight, the baffling source of its gamma-ray emissions. Right at the galaxy's core, where the supermassive black hole reigns, astronomers detect a relentless torrent of gamma rays, the most energetic light in the universe. Yet, despite decades of observation, their precise origin remains shrouded in uncertainty. Is this radiation screaming from the black hole itself, or could it stem from a bustling crowd of stars and compact objects lurking nearby? To grasp why this mystery matters, consider gamma rays as cosmic fingerprints. Each source leaves a distinct mark. If the black hole is the culprit, its emissions would likely fluctuate wildly, tied to the chaotic dance of matter spiraling into oblivion. Imagine a flickering light bulb dimming and brightening as power surges. Yet the gamma-ray signal from Centaurus A shows both steady and variable components, as if two actors share the stage. One possibility is that the black hole's jet, pumping out particles at near light speeds, collides with surrounding gas, creating shock waves that glow in gamma rays. In this scenario, the jet acts like a cosmic particle accelerator, slamming electrons into photons and boosting them to extreme energies. But there's another contender, a dense, star-packed cluster huddled near the black hole. Such clusters, known as nuclear star clusters, are common in galaxy centers and can harbor thousands of stars crammed into a tiny volume. Among them, rapidly spinning neutron stars called pulsars, or even elusive magnetars with crushing magnetic fields, could be churning out gamma rays. Picture a swarm of fireflies, each flickering unpredictably. Collectively, their light might blend into a steady glow with occasional flares. Supporting this idea, some galaxies without active black holes still emit gamma rays, suggesting stellar processes can mimic a black hole's signature. The stakes are high. If the black hole dominates, it would underscore its role as the galaxy's ultimate power broker, shaping everything from gas flow to cosmic ray production. But if stars steal the spotlight, it challenges assumptions about how gamma rays trace black hole activity. Recent observations complicate things further. Gamma-ray hotspots sometimes appear offset from the black hole's exact position, hinting at unseen structures or even multiple sources. The Fermi Gamma-Ray Space Telescope has mapped these emissions in detail, yet the data refuses to settle the debate cleanly. One tantalizing clue lies in the energy spectrum of the gamma rays. Black hole jets tend to produce a characteristic cutoff at high energies, while star clusters might generate a smoother distribution. Current measurements hover between these predictions, leaving room for both or neither explanation. Upcoming instruments like the Cherenkov Telescope Array aim to resolve finer details, potentially isolating individual sources within the core's turmoil. What's certain is that Centaurus A's gamma-ray core defies simple answers. It forces us to confront the limits of our cosmic vision, where even the most advanced telescopes struggle to untangle overlapping signals. Whether the black hole or a stellar frenzy fuels this radiation, the solution will rewrite how we interpret similar emissions across the universe. And as we peer deeper, we're reminded that sometimes the brightest cosmic beacons cast the most tangled shadows. Now, stepping into another intriguing puzzle within Centaurus A, we come face to face with a curious void in its stellar timeline, a missing generation of stars. Unlike most galaxies, where stars of various ages mingle like a crowd spanning generations, Centaurus A shows a striking gap. Its stars are either ancient relics or youthful newcomers, with remarkably few in between. This absence of middle-aged stars hints at a dramatic pause in star formation, as if the galaxy took a cosmic breather before reigniting its stellar factories. To understand why this gap matters, picture a bustling city where suddenly, for decades, no children are born. The population would skew heavily toward the elderly and the very young, leaving a conspicuous blank space in the middle. Similarly, stars in galaxies form continuously unless something disrupts the process. In Centaurus A, the lack of stars around 500 million to 5 billion years old suggests a prolonged hiatus, a period when the gas needed to create new stars was either blocked, depleted, or violently expelled. One leading theory points to the galaxy's violent merger history. When Centaurus A collided with a smaller galaxy roughly 1 billion years ago, the gravitational chaos could have disrupted its gas reservoirs. Mergers often trigger bursts of star formation as gas clouds compress, but they can also fling gas outward, starving the galaxy of fuel. Imagine a whirlwind sweeping through a workshop, scattering tools and materials. Some might be piled into new structures while others are lost entirely. In this case, the merger might have cleared out the gas so thoroughly that star formation stalled for eons, creating the age gap we see today. Alternatively, the supermassive black hole at the galaxy's core could be the culprit. Active black holes emit powerful jets and radiation that can heat or eject surrounding gas, preventing it from cooling and collapsing into stars. Think of a furnace blasting hot air into a nursery. No seedlings could take root. If Centaurus A's black hole went through a particularly aggressive phase during this period, it might have suppressed star formation long enough to leave a void in the stellar record. Yet another possibility involves dark matter. If the galaxy's dark matter halo underwent a major reshuffling, perhaps due to a close encounter with another halo, it could have altered the gravitational environment, disrupting gas flow. Dark matter doesn't interact with light, but its gravitational pull shapes how ordinary matter moves. A sudden shift could have diverted gas away from star-forming regions, like a hidden hand tilting a cosmic scale. Intriguingly, the end of this star-forming drought coincides with the galaxy's current burst of youthful stars. Some event, maybe residual gas settling back into place or a fresh influx from another merger, reignited the process. This resurgence adds another layer to the mystery. Why did star formation restart so vigorously? The answer might lie in the galaxy's complex dance of mergers, black hole activity, and dark matter dynamics, each leaving its mark on the stellar population. What makes Centaurus A's age gap especially fascinating is how it mirrors gaps seen in other massive galaxies, suggesting this isn't a fluke but a clue to broader galactic behavior. By studying this void, astronomers can piece together how external shocks and internal processes collaborate to shape a galaxy's life story. The next generation of telescopes, like the James Webb Space Telescope, could analyze the chemical composition of these stars in finer detail, revealing what elements were present or absent during the quiet epoch. Centaurus A's missing middle-aged stars are more than just a demographic oddity. They're a cosmic breadcrumb trail leading us toward answers about how galaxies evolve through violence, silence, and rebirth. And as we trace that trail, we're reminded that even the quietest chapters in a galaxy's history can shout the loudest secrets. Now, shifting our gaze to an even more baffling feature, let's delve into the whispers of Centaurus A's so-called double nucleus. Some observations suggest this galaxy might be hiding not one but two bright cores at its heart. Could this be a trick of the light, a cosmic illusion caused by thick dust lanes twisting our view? Or is it concrete evidence of a recent galactic merger, leaving behind a pair of supermassive black holes locked in a gravitational dance? At first glance, the idea of a double nucleus seems improbable. After all, galaxies typically host a single supermassive black hole at their center, but Centaurus A is anything but typical. high-resolution images, particularly in infrared and radio wavelengths, reveal what appears to be two distinct bright spots separated by a few hundred light-years. One possibility is that we're seeing light from the primary black hole's accretion disk, with its glow split and distorted by the galaxy's infamous dust lanes. Think of it like shining a flashlight through a dense fog. The beam might appear fragmented, creating the illusion of multiple sources. However, there's another, far more dramatic explanation. If Centaurus A recently merged with another galaxy, it's possible the incoming galaxy brought its own supermassive black hole along for the ride. Over time, the two black holes would spiral toward each other, eventually forming a binary system. During this process, they'd emit intense radiation as they fed on surrounding gas, creating the appearance of dual cores. This scenario isn't just science fiction, it's a well-documented phase in galactic evolution. In fact, astronomers have spotted similar double nuclei in other merging galaxies, like NGC 6240. But how do we determine which explanation holds true for Centaurus A? One clue lies in the motion of gas and stars near the cores. If there are indeed two black holes, their gravitational pull would stir up the surrounding material in distinct ways. Recent studies using the Atacama Large Millimeter Array have detected unusual gas movements in the galaxy's center, with some streams appearing to orbit a second unseen mass. Yet, the evidence isn't definitive. The dust obscuration is so severe that even our most advanced telescopes struggle to peer through it clearly. Adding to the intrigue, the two bright spots don't behave identically. One emits stronger radio waves typical of an active black hole jet, while the other shines more brightly in infrared, suggesting heated dust. This discrepancy could imply that one core is the true black hole, while the other is a dense knot of star formation ignited by the merger's shockwaves. Alternatively, both could be black holes at different stages of activity, with one fueling a jet while the other is temporarily quiet. The implications of a double nucleus extend beyond mere curiosity. If Centaurus A does harbor two supermassive black holes, their eventual collision would send ripples through space-time itself, gravitational waves detectable by observatories like LIGO. Moreover, studying such systems helps us understand how galaxies grow through mergers. Every time two galaxies combine, their black holes must eventually coalesce, but the process can take billions of years. Catching them in the act, as we might be doing here, offers a rare glimpse into this cosmic choreography. For now, the double nucleus remains an open question. Future observations with next-generation instruments, like the extremely large telescope, could finally settle the debate by piercing through the dust with unprecedented clarity. Whether it's an illusion or a genuine pair of black holes, the answer will reshape our understanding of Centaurus A's turbulent past and the forces that continue to sculpt it today. So keep your eyes on the cosmos, because this galaxy still has plenty of secrets left to reveal. Now, let's turn our attention to another astonishing capability of Centaurus A, its potential role as a cosmic ray factory. This galaxy might be one of the universe's most powerful natural accelerators, hurling particles across space at nearly the speed of light. But how does it achieve such extreme feats, and what does this tell us about the hidden mechanics of active galaxies? Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that zip through space at mind-bending velocities. While some originate from supernova or the Sun, the most energetic ones likely come from distant astrophysical powerhouses like Centaurus A. Here's where the galaxy's colossal jets enter the picture. Stretching over millions of light-years, these jets are more than just spectacular light shows. They're particle accelerators on an unimaginable scale. The secret lies in the chaos surrounding the supermassive black hole. As matter spirals into the black hole's accretion disk, powerful magnetic fields twist and snap, channeling some of the material into ultra-fast jets. Within these jets, particles get caught in shock waves, cosmic versions of sonic booms created by collisions or instabilities in the outflowing plasma. These shocks act like natural accelerators, repeatedly boosting particles to higher energies. Imagine a pinball ricocheting between bumpers, gaining speed with each hit. Now scale that up to the size of a galaxy, and you've got Centaurus A's particle acceleration process. But why does this matter? For decades, scientists have puzzled over the origins of ultra-high-energy cosmic rays, which can pack millions of times more energy than anything produced in human-made colliders. Centaurus A, being the closest active galaxy to Earth, offers a front-row seat to study this phenomenon. Detectors like the Pierre Auger Observatory have traced some of these extreme particles back to the general direction of Centaurus A, though pinpointing their exact source remains tricky due to cosmic rays being deflected by magnetic fields during their journey. What's especially fascinating is how Centaurus A's jets compare to other cosmic accelerators. While supernova can generate cosmic rays, they rarely reach the energies observed from active galaxies. The difference, scale and environment. Centaurus A's jets operate in a far more violent setting, with magnetic fields orders of magnitude stronger and regions of acceleration spanning vast distances. This allows particles to keep gaining energy over longer periods, like a surfer riding an endless wave. Yet mysteries linger. For instance, not all cosmic rays from Centaurus A may come directly from its jets. Some could be produced when jet particles collide with interstellar gas, sparking cascades of secondary particles. Others might originate in the galaxy's turbulent lobes, where magnetic fields remain strong enough to sustain acceleration long after the initial jet material has traveled far from the core. The implications stretch beyond astrophysics. If Centaurus A is indeed a dominant source of high-energy cosmic rays, it could help explain rare, puzzling events on Earth, like atmospheric particle showers with energies exceeding 100 million billion electron volts. Understanding these processes also sheds light on how black holes redistribute energy across the cosmos, shaping everything from star formation to the evolution of galaxy clusters. Looking ahead, new telescopes like the Cherenkov Telescope Array aim to catch gamma rays, the telltale byproducts of cosmic ray interactions, with unprecedented precision. These observations could finally confirm Centaurus A's role in the cosmic ray puzzle. Whether as a primary factory or a contributing player, this galaxy's ability to launch particles across the universe reminds us of the raw power lurking in the hearts of active galaxies and the secrets they still hold. Now, let's shift our gaze to one of Centaurus A's most striking features, those dramatic, dark dust lanes slicing across its center. But here's the twist: these lanes aren't just static scars from a long-ago collision. New evidence suggests they might be on the move, reshaping themselves over time. What could be causing this cosmic makeover? When astronomers compare decades-old images of Centaurus A with modern observations, they notice subtle but significant shifts in the dust lane structure. Some sections appear to twist or stretch, while others fade or thicken. This isn't just a trick of the light, it's a real transformation happening on a galactic scale. The question is, what's driving it? One leading theory points to the aftermath of the galaxy's ancient mergers. Centaurus A is a cosmic cannibal, having devoured smaller galaxies in the past. The dust lanes we see today are likely debris from those violent encounters, like swirls in a pond after a stone's thrown in. But unlike a pond settling into stillness, Centaurus A's chaotic environment keeps stirring the pot. The supermassive black hole's gravitational pull, combined with the orbits of surviving stars and gas clouds, could be tugging at these dust lanes, warping them over centuries. Yet there's another possibility: internal dynamics. Gas and dust within the galaxy don't just sit quietly, they swirl, collide, and form dense clumps. Magnetic fields, stellar winds, and even newborn stars can push and pull on the surrounding material, altering the dust lane's shape. Imagine a handful of sand tossed into a whirlpool. the grains don't stay put, they're dragged along by currents invisible to the eye. Similarly, Centaurus A's dust might be responding to hidden forces within its own structure. The most intriguing clue comes from the dust lane's alignment with the galaxy's radio jets. Some studies suggest the jet's immense energy could be heating or displacing nearby dust, creating localized changes. It's like holding a blowtorch to a sheet of ice. The ice doesn't just melt evenly, it cracks and shifts in unexpected ways. If the jets are indeed interacting with the dust, it would mean Centaurus A's black hole isn't just a passive observer but an active sculptor of its surroundings. But proving this isn't easy. Dust lanes are notoriously tricky to study because they obscure the light behind them, like trying to map the contours of a shadow. Astronomers rely on infrared and radio observations to peer through the veil, piecing together changes over time. Recent advances in telescope resolution, like those from the James Webb Space Telescope, are finally offering crisp enough images to track these subtle evolutions year by year. Why does this matter? Dust lanes aren't just cosmetic, they're factories for future stars. As dust compresses, it can collapse into star-forming regions. If the lanes are shifting, so too might the sites where new stars ignite. Plus, understanding their motion helps unravel the galaxy's deeper history, like reading wrinkles on a face to guess a lifetime of smiles and frowns. The debate continues. Are we watching the slow ripple of a past merger or the churn of a galaxy reinventing itself from within? Either way, Centaurus A's restless dust lanes remind us that even the most ancient structures in the universe are never truly still. Every shift, every twist is a clue waiting to be decoded, a whisper from a galaxy that refuses to stay silent. With this puzzle still unfolding, let's turn to another enigma. The missing dwarf galaxies that ought to orbit Centaurus A but seem to have vanished without a trace. Where did they go, and what does their absence reveal about this galaxy's dark secrets? Now, let's tackle one of Centaurus A's most baffling mysteries, the case of the missing dwarf galaxies. Unlike our Milky Way, which is surrounded by dozens of these small galactic companions, Centaurus A appears oddly lonely. Where did they go, and what does their absence tell us about this galaxy's violent past? The Milky Way's entourage of dwarf galaxies, like the large and small Magellanic Clouds, are cosmic leftovers from the early universe. They're faint, ancient, and orbit larger galaxies like bees around a hive. But Centaurus A, its neighborhood is eerily quiet. Astronomers have searched tirelessly, yet only a handful of dwarf galaxies have been spotted nearby. This isn't just a coincidence, it's a clue. One explanation points to Centaurus A's supermassive black hole. With its monstrous gravity and energetic jets, this black hole could have torn apart any dwarf galaxies that ventured too close. Imagine a cosmic shredder. Small galaxies straying into its grasp would be stretched, stripped of their stars, and eventually swallowed whole. The black hole's jets might have also blasted away the gas needed for these dwarfs to form new stars, leaving them too dim to detect. But there's another, even darker suspect: mergers. Centaurus A's history is written in the scars of past collisions. Each time it devoured a smaller galaxy, the chaos could have disrupted or destroyed orbiting dwarfs. Gravitational tugs from these mergers might have flung them into deep space or scattered their stars into Centaurus A's halo. Think of it like a game of billiards. Every collision sends smaller objects careening in unpredictable directions. Some astronomers propose a third possibility. The dwarfs are there, just hiding. Centaurus A's thick dust lanes and bright core could be obscuring them, making them invisible to our telescopes. Or perhaps they're made of mostly dark matter with too few stars to notice. Recent surveys using ultra-sensitive instruments are scanning the galaxy's outskirts, hoping to spot these elusive shadows. The absence of dwarf galaxies isn't just a curiosity, it's a window into how galaxies evolve. Dwarfs are building blocks of the universe, and their fate shapes the growth of giants like Centaurus A. If they were destroyed, it reveals the sheer power of its black hole. If they were ejected, it shows how mergers rewrite galactic landscapes, and if they're hiding, it challenges our tools and theories. As we piece together this cosmic whodunit, let's turn to another puzzle, the strange, transitional phase Centaurus A seems to be in, caught between youth and old age. What does its green valley status tell us about the life cycle of galaxies? Shifting our gaze to another cosmic puzzle, let's explore Centaurus A's peculiar green valley status, a phase that places it neither among the vibrant, star-forming galaxies nor the quiet, dead ones. This transitional stage offers a rare glimpse into how galaxies evolve over billions of years, and Centaurus A might just hold the key to understanding this cosmic metamorphosis. Most galaxies fall into two clear categories. On one end, there are the blue galaxies, bustling with young, hot stars and clouds of gas where new stars are born. On the other, red galaxies where star formation has all but ceased, leaving behind older, cooler stars. But Centaurus A, it's caught in between, in what astronomers call the Green Valley, a cosmic limbo where galaxies slowly shut down their star-forming engines. What makes this phase so intriguing is that it's relatively short-lived in galactic terms. Think of it as a galaxy's midlife crisis. The frenetic star-making of its youth is winding down, but it hasn't yet settled into the quiet retirement of old age. For Centaurus A, this transition might be linked to its violent history. The galaxy's past mergers and its supermassive black hole's relentless activity could be draining its gas reserves, the fuel needed to create new stars. Without fresh gas, star formation sputters out, leaving the galaxy to fade slowly into the red category. But here's where it gets even more fascinating. Unlike many Green Valley galaxies, Centaurus A isn't entirely passive. Its dust lanes and pockets of star formation suggest it's still clinging to some youthful vigor, even as its core grows quieter. This duality hints that the shutdown process isn't always smooth or uniform. Some parts of the galaxy might be running out of gas faster than others, creating a patchwork of activity and stillness. So why does this matter? Studying Centaurus A's Green Valley phase helps astronomers piece together the final chapters of a galaxy's life. It's like finding a missing link in the evolutionary chain. By observing how it transitions, we can better predict the fate of other galaxies, including our own Milky Way. One day, even our galaxy will enter this phase, its star formation slowing as it drifts toward the red category. As we unravel the secrets of Centaurus A's twilight years, another layer of mystery awaits. How its polarized radio light reveals hidden structures in its turbulent magnetic fields. Now, let's turn our attention to something even more elusive, the polarized radio light streaming from Centaurus A's colossal lobes. These faint, ghostly emissions aren't just random noise. They carry a hidden signature, a cosmic fingerprint that reveals the invisible forces shaping this galaxy. What makes these radio waves so special? They're polarized, meaning their light waves vibrate in a specific, organized direction rather than chaotically. It's like looking at sunlight reflecting off a lake. The glare you see is often polarized, creating a distinct pattern. But in Centaurus A's case, the patterns are far more mysterious, and they tell a story about the galaxy's turbulent heart. The polarization we detect isn't uniform. Instead, it twists and turns across the radio lobes, creating intricate swirls and abrupt changes in alignment. This chaos isn't random, it's a direct result of the magnetic fields tangled within the lobes. Imagine throwing a handful of iron filings onto a magnet. The filings align along the magnetic field lines, revealing their structure. In Centaurus A, the polarized light acts like those filings, tracing out the otherwise invisible magnetic fields woven through the galaxy's massive radio lobes. These magnetic fields aren't just passive spectators. They play a crucial role in shaping the jets surging from the galaxy's supermassive black hole. As the jets plow through space, they drag these magnetic fields along, stretching and twisting them like taffy. The turbulence in the jets caused by collisions with intergalactic gas or instabilities in their flow further scrambles these fields, creating the patchy polarization patterns we observe. Some areas show tightly aligned waves, suggesting strong, ordered fields, while others are a jumbled mess, hinting at regions where the magnetic chaos reigns supreme. But why does this matter? Polarized light doesn't just reveal magnetic fields. It helps us understand how energy escapes from the galaxy. The black hole's jets dump enormous amounts of energy into the lobes, but without magnetic fields, that energy would dissipate too quickly to form the vast structures we see. The fields act like cosmic containment vessels, channeling and storing the energy, allowing the lobes to grow to millions of light years across. They're the reason Centaurus A's radio glow persists long after the initial outbursts from the black hole. There's even a tantalizing possibility that these polarized patterns hold clues about something even more profound: the origins of cosmic magnetism itself. Did these fields arise from the galaxy's violent mergers, or were they seeded in the early universe and amplified by the black hole's fury? Each twist in the polarization offers a piece of the puzzle. As we decode these luminous signatures, another layer of Centaurus A's drama comes into focus: how its obscured active nucleus hides secrets behind a curtain of dust. Now let's peer through the cosmic dust that shrouds Centaurus A's most secretive feature, its active nucleus. This is no ordinary black hole. It's a monstrous engine of energy, but one that hides behind thick curtains of dust and gas. From our vantage point on Earth, the direct light from this beast is completely blocked, as if nature itself has drawn a veil over its most violent spectacle. But astronomers have a trick up their sleeves. They don't rely on visible light to study it. Instead, they turn to the silent whispers of infrared and the piercing gaze of X-rays to reveal what's hidden. Infrared light is the key to unlocking this dusty enigma. Unlike visible light, which gets absorbed or scattered by the dust, infrared radiation slips right through. It's like using night vision goggles to see in complete darkness. Telescopes like the Spitzer Space Telescope and the James Webb Space Telescope capture this faint glow, painting a picture of the chaotic region around the black hole. The dust isn't just a passive barrier, it's heated by the intense radiation from the black hole's accretion disk, glowing brightly in infrared. This allows astronomers to map the structure of the dust lanes, unraveling how they twist and funnel material toward the black hole. But infrared alone can't tell the whole story. To truly probe the heart of the beast, we need X-rays. These high-energy photons are produced in the most violent environments imaginable, near the event horizon, where matter spirals into oblivion at nearly the speed of light. Instruments like NASA Chandra X-ray Observatory detect these signals, which punch straight through the dust like bullets through tissue paper. The X-rays reveal the temperature of the gas, the speed of the inflowing material, and even the magnetic fields that whip particles to extreme energies. Combining these two views gives us a complete picture. The infrared shows us the dust structure, while X-rays expose the raw power of the black hole's feeding frenzy. Together, they've uncovered something startling. Despite the thick shroud, the black hole's influence is anything but hidden. Jets of plasma, powered by the black hole's spin, blast outward, carving through the dust and shaping the galaxy itself. Even the polarized radio emissions we discussed earlier trace back to this obscured nucleus, proving that no amount of dust can fully contain its fury. The obscuration isn't just a challenge, it's a clue. The very presence of so much dust hints at a turbulent past. Some theories suggest it's debris from a galactic merger, while others propose it's the remnants of countless stars torn apart by the black hole's gravity. Whatever its origin, this dusty veil is a dynamic part of Centaurus A's story, not just a barrier but a character in its own right. As we piece together these observations, one thing becomes clear: the nucleus may be hidden, but its influence is unmistakable. Every wavelength of light, from infrared to X-rays, tells a different part of the tale. revealing how even the most secretive corners of the universe can't escape our curiosity. And with that, we turn our attention to another puzzle: the strange way any dwarf galaxies around Centaurus A seem to align, as if pulled by unseen strings. Now let's shift our gaze to the outskirts of Centaurus A, where something peculiar is happening among its smaller neighbors. Dwarf galaxies, those faint cosmic companions orbiting larger galaxies like Centaurus A, aren't supposed to fall into neat patterns. Yet here they appear to align in a way that defies randomness, almost as if an invisible hand has arranged them. This isn't just a curiosity, it's a potential window into the hidden architecture of the universe sculpted by dark matter. Dwarf galaxies are typically scattered haphazardly around their larger hosts, like crumbs dropped around a dinner plate. But around Centaurus A, they seem to cluster along a preferred plane or even line up in a rough disk. At first glance, this might seem like a coincidence, but the odds of such an alignment happening by chance are astronomically low. So what's really going on? One compelling explanation points to dark matter, the mysterious substance that makes up most of the universe's mass but refuses to interact with light. Dark matter isn't just a passive backdrop, it shapes the cosmos on grand scales. Simulations of galaxy formation show that dark matter halos the vast, invisible cocoons surrounding galaxies, can channel smaller galaxies into orbits that mirror their own structure. If Centaurus A's dark matter halo is flattened or elongated like a cosmic lens, it could naturally herd its dwarf satellites into aligned paths. This wouldn't just explain their arrangement, it would also give us clues about the halo's shape, something we can't observe directly. But there's another twist. Some astronomers argue that this alignment might be a fossil of Centaurus A's violent past. If the galaxy grew by cannibalizing smaller neighbors, the dwarfs we see today could be survivors of a larger group that once orbited in a shared plane, their orbits preserved over billions of years. Alternatively, the alignment might hint at a recent interaction with another massive galaxy, one that stirred up the dwarfs like leaves caught in a whirlwind. The debate is far from settled. Skeptics point out that our view of these dwarfs is limited. Dust and distance make them hard to study, and we might be missing some that don't fit the pattern. Others suggest that the alignment could be a temporary fluke, a snapshot of a dynamic system that will eventually scatter into chaos. But if dark matter is indeed the sculptor, this alignment could be a rare glimpse into its influence, a cosmic fingerprint left on the visible universe. What makes this mystery so tantalizing is its stakes. If the dwarf's alignment is proof of dark matter's gravitational choreography, it could help us understand how all galaxies, including our own Milky Way, assemble and evolve. But if it's a relic of past collisions, it tells a story of Centaurus A's turbulent history, written in the orbits of its smallest companions. Either way, these faint galaxies are more than just specks of light. They're storytellers, revealing secrets about forces we can't see. And with that, we turn to another enigma: the cold reservoirs of gas that somehow survive near Centaurus A's furious core, defying the black hole's heat. How do these fragile clouds endure in such a hostile environment? The answer might lie in the delicate balance between destruction and creation. Now, let's venture into one of Centaurus A's most baffling contradictions: the existence of cold hydrogen clouds thriving just beyond the reach of its supermassive black hole's destructive power. It's like finding ice cubes in a furnace, defying everything we know about extreme environments. At the galaxy's core, temperatures soar to millions of degrees as the black hole's jets blast out energy, shredding nearby gas and dust. Yet, against all odds, pockets of cold molecular hydrogen, the raw material for star formation, persist in this cosmic war zone. How can something so delicate endure such violence? The answer lies in a delicate dance between chaos and resilience. These cold gas reservoirs aren't just random survivors, they're shielded by their own structure. Imagine a sponge floating in a stormy sea. The densest knots of gas act like shock absorbers, their tightly packed molecules resisting the black hole's heat. Surrounding layers of cooler gas further insulate them, creating a protective cocoon. Meanwhile, turbulence from the jets might actually help, compressing the gas in some regions and triggering the formation of these cold pockets. It's a cosmic irony. The same forces that destroy can also create sanctuaries. But there's another twist. Some of this cold gas could be fresh arrivals, funneled into the galaxy's center by its own gravity. As gas clouds spiral inward, they don't all plunge directly into the black hole's maw. Instead, collisions between clouds can slow them down, allowing some to settle into stable orbits or even form a rotating disk. This disk, much like the calm eye of a hurricane, provides a refuge where temperatures stay low enough for hydrogen molecules to survive. Astronomers have also spotted another clue: filaments of dust winding through the chaos. These dusty tendrils might act like sunshades, blocking the intense radiation from the black hole and creating shadowed regions where gas can cool. Similar structures appear in other active galaxies, suggesting this could be a universal survival tactic for cold gas in hostile environments. The implications are profound. If cold gas can withstand such extremes, it means star formation might still be possible even in the most turbulent galactic cores. Centaurus A's stubborn reservoirs challenge our assumptions about how black holes influence their surroundings, revealing a universe where creation and destruction exist side by side. And this brings us to another layer of the mystery: the knotted, uneven structure of the galaxy's jets themselves, which might hold the key to why these cold pockets form in the first place. Now, let's unravel the tangled mystery of Centaurus A's clumpy jets. Unlike the sleek, streamlined outflows we might expect from such a powerful black hole, these jets are riddled with bright, uneven knots, like a string of cosmic pearls glowing with intense energy. What causes these chaotic structures, and what do they reveal about the hidden forces at work? The answer lies in the turbulent journey of the jets themselves. As material is hurled outward at nearly the speed of light, it doesn't travel smoothly. Instead, it encounters shocks, violent collisions within the jet or against surrounding gas. Picture a high-speed train suddenly hitting a series of bumps. Each jolt compresses the jet's particles, heating them up and causing them to glow brighter in X-rays and radio waves. These shock-borne knots are like cosmic road markers, tracing where the jet has faced resistance. But shocks aren't the only culprit. Instabilities in the jet's magnetic fields can also twist and kink its flow, much like a garden hose thrashing uncontrollably when water pressure surges. The black hole's spin and the disk's turbulent environment create a feedback loop where magnetic fields tangle, snap, and reconnect. This releases bursts of energy, forming those telltale bright spots. Some astronomers even compare it to lightning within the jet, sudden, fierce, and unpredictable. The knots might also hint at the black hole's feeding habits. If the black hole gulps down matter unevenly, in fits and starts rather than a steady stream, the jets could reflect this erratic diet. Clumps of material falling inward might trigger corresponding outbursts in the jets, leaving behind these glaring knots as evidence of past feasts. It's a cosmic echo of the chaos at the galaxy's heart. Interestingly, the spacing between these knots isn't random. Some studies suggest they follow a pattern, like ripples from a stone tossed into a pond. This could mean the black hole's accretion disk has rhythmic oscillations, perhaps caused by orbiting clumps of gas or even a hidden companion black hole tugging at the disk's edge. Each oscillation might send a new wave of energy down the jet, lighting up another knot in the chain. What's more, these structures aren't static. Over years or decades, astronomers have watched some knots move, fade, or even merge. This dynamism suggests the jets are alive with activity, constantly reshaped by the black hole's whims. It's a far cry from the steady, unchanging beams we once imagined. Centaurus A's knotted jets challenge our textbook models of how black holes interact with their surroundings. They show us that even the most powerful outflows in the universe are messy, unpredictable, and full of surprises, much like the galaxy itself. Now, shifting our gaze to another enigma, let's explore the peculiar case of Centaurus A's metallicity gradient, a cosmic fingerprint revealing how the galaxy's metal content varies in unexpected ways. Unlike most galaxies, where heavier elements like iron and oxygen smoothly decrease from the crowded core to the sparse outskirts, Centaurus A's metals are distributed in a patchwork, as if someone scattered them unevenly across its vast expanse. This irregularity isn't just a curiosity, it's a clue pointing to the galaxy's turbulent past and the chaos of its star-forming regions. To understand why this matters, imagine a city where wealth isn't concentrated downtown but scattered in random pockets. In galactic terms, wealth translates to metals elements forged in the hearts of stars and scattered by supernova. Normally, older stars in a galaxy's core are richer in metals because they formed from recycled material ejected by countless generations of stars. But in Centaurus A, some outer regions are curiously metal-rich, while parts of the inner galaxy are surprisingly poor. This inverted or disjointed pattern defies expectations, and the explanation likely lies in the galaxy's violent merger history. When Centaurus A collided with a smaller galaxy eons ago, it didn't just warp its dust lanes, it stirred up its stellar chemistry. The merger could have flung metal-rich stars outward, like splashing paint across a canvas, while dragging metal-poor gas from the victim galaxy into Centaurus A's core. Computer simulations support this. Galactic collisions often create these chaotic metallicity maps, as stars and gas from different origins mix unevenly. It's as if Centaurus A's history is written in the mismatched metal content of its stars, a record of the cosmic upheaval it endured, but mergers aren't the only factor at play. The galaxy's uneven star formation adds another layer to the mystery. In regions where star birth has been intense, supernovae have enriched the gas with metals, creating localized hotspots. Elsewhere, quieter zones have missed out on this pollution, leaving their stars with a more primordial, metal-poor composition. This patchiness suggests that star formation in Centaurus isn't just violent but also erratic, flaring up in bursts rather than as a steady process. Adding to the intrigue, astronomers have spotted metal-poor gas clouds near the galaxy's core, a rarity in most massive galaxies. One theory is that these are ancient leftovers from the pre-merger era, pockets of gas that avoided contamination by metal-producing stars. Another possibility, the black hole's jets might have cleared out metal-rich gas in some areas, leaving behind these odd, pristine clouds. Either way, these anomalies force us to rethink how galaxies accumulate and distribute their heavy elements over time. What makes Centaurus A's metallicity gradient truly fascinating is how it connects the dots between cosmic collisions, black hole activity, and star formation. It's a reminder that galaxies aren't static museums of stars but dynamic, ever-evolving systems where even something as fundamental as metal content can tell a story of chaos and renewal. As we piece together these clues, we're not just mapping a galaxy, we're reading its autobiography, written in the language of elements scattered across the cosmos. Now, turning our attention to an even deeper layer of this galactic mystery, let's examine the ghostly whispers of Centaurus A's past, the so-called fossil radio emissions. These faint, sprawling structures are like echoes from a bygone era, remnants of the supermassive black hole's ancient outbursts that have lingered for millions of years. Unlike the bright, active jets we see today, these fossil emissions are the faded signatures of previous eruptions, offering us a rare glimpse into the black hole's long-term behavior. Imagine stumbling upon an ancient battlefield where the weapons have rusted but the scars on the land remain. In the same way, these fossil radio structures are the scars of past cosmic violence. Stretching far beyond the galaxy's visible boundaries, they tell us that Centaurus A's black hole wasn't always as quiet as it appears now. it once unleashed titanic energies capable of shaping its surroundings on an unimaginable scale. By studying these faint signals, astronomers can piece together a timeline of the black hole's most violent phases, much like geologists reading layers of rock to understand Earth's history. What makes these fossil emissions particularly fascinating is their sheer longevity. Unlike the temporary glow of a supernova or the flickering light of a star, these radio echoes persist for staggering amounts of time, often outlasting the galaxies they originated from. The reason: the particles ejected during past black hole outbursts travel at nearly the speed of light, spreading across vast distances and interacting with the intergalactic medium. Over eons, they slow down but don't entirely disappear, leaving behind these diffuse radio halos that modern telescopes can still detect. But how do we know these emissions aren't just leftovers from the current jets? The key lies in their structure and energy. Fossil radio lobes are usually much broader and fainter than active ones, lacking the tight, energetic beams we see in Centaurus A's present-day jets. Some even show signs of being re-energized by newer outbursts, creating a layered effect, like an old painting touched up by a later artist. This suggests that the black hole has gone through multiple cycles of activity and dormancy, each outburst adding a new chapter to its history. One of the most compelling theories is that these fossil emissions could help explain why Centaurus A's surroundings seem so unusually empty. Few dwarf galaxies orbit it compared to similar massive galaxies, and some researchers speculate that past jets might have blown away neighboring gas clouds or even stripped smaller galaxies of their star-forming material. If true, these faint radio ghosts aren't just relics, they're evidence of a black hole so powerful it reshaped its entire cosmic neighborhood. The next time you look at an image of Centaurus A, remember, what we see today is just a snapshot. Hidden in those faint radio whispers are eons of explosive history waiting to be decoded, and as astronomers develop more sensitive telescopes, we may soon uncover even older outbursts, revealing just how far this galaxy's influence truly extends. But here's a puzzle that has astronomers scratching their heads. Why are some regions of Centaurus almost eerily empty when they should be teeming with molecular gas? These cold, dense clouds of hydrogen and other molecules are the raw materials for star formation, and yet in certain parts of the galaxy they're conspicuously absent. The question is, where did they go? One leading theory points to the galaxy's supermassive black hole and its monstrous jets. Think of these jets as cosmic blowtorches, capable of carving through gas clouds with unimaginable force. If a jet plows through a region rich in molecular gas, the energy it releases could heat the gas to such extreme temperatures that it disperses or even gets blasted entirely out of the galaxy. Essentially, the black hole's tantrums might have swept its own kitchen clean, leaving behind voids where new stars should have been born. But there's another intriguing possibility. Perhaps the gas isn't missing at all. Instead, it might be hiding in plain sight, camouflaged within thick veils of dust. Centaurus A is notorious for its dark, tangled dust lanes, which could be obscuring vast reservoirs of cold molecular gas from our telescopes. Just like trying to spot a snowstorm behind a foggy window, some of these gas clouds might simply be invisible at certain wavelengths. Only by observing in infrared or radio frequencies light that can pierce through dust can astronomers hope to uncover these hidden treasures. The mystery deepens when we consider that not all gas behaves the same way. Some regions might have gas that's too hot or too diffused to form stars, while other pockets could be shielded from the black hole's fury by sheer luck of their location. It's also possible that past galactic mergers stirred the gas up, redistributing it unevenly across Centaurus A. Imagine pouring cream into coffee but then swirling it violently. Some areas end up richer than others. Whatever the explanation, the absence of molecular gas in certain zones has real consequences. Fewer gas clouds mean fewer new stars, potentially altering the galaxy's evolution over time. And if the black hole is indeed responsible for clearing out these regions, it raises a fascinating question: just how much influence can a single supermassive black hole have on its entire galactic ecosystem? As astronomers refine their observations, the truth may lie somewhere in between. A mix of destruction, concealment, and cosmic turbulence. One thing's for certain: Centaurus A never fails to remind us that even the emptiest corners of space can hold the most tantalizing secrets. Now let's turn our attention to something that seems almost ghostly, an eerie glow surrounding Centaurus A that only reveals itself in infrared light. When astronomers pointed the Spitzer Space Telescope at this galaxy, they detected a vast, faint halo stretching far beyond its visible edges. This cosmic shroud raises an immediate question: what exactly are we seeing? Is this the scattered remains of ancient stars, or could it be dust lingering from past galactic collisions? One compelling explanation points to starlight not from living stars but from long-dead ones. Over billions of years, countless stars in Centaurus A have burned out, leaving behind dim, aging stellar remnants. These ancient stars no longer shine brightly in visible light, but their faint warmth still leaks out as infrared radiation. If this halo is truly made of these stellar ghosts, it would mean we're looking at the galaxy's extended graveyard, a relic of its earliest days when star formation was rampant. But there's another possibility: this glow might come from dust, not stars. When galaxies collide, violent forces can hurl dust far beyond their main bodies. In Centaurus A's case, past mergers could have scattered fine dust particles into its outer reaches, where they now catch and re-emit light from the galaxy's core. Picture holding a dusty lampshade up to a light bulb. The farther you stand, the fainter the glow. Similarly, this dust could be reflecting and diffusing the galaxy's light, creating that faint infrared halo. Then there's the wildcard idea: could it be both? Some researchers suggest the halo might be a mix of these two components, with dust and ancient stars coexisting in the galaxy's outskirts. The challenge is untangling their signals. Dust tends to emit at slightly different infrared wavelengths than old stars, so detailed spectral analysis might one day settle the debate. What makes this mystery so important is what it tells us about galactic evolution. If the halo is mostly stars, it implies Centaurus A grew by cannibalizing smaller galaxies long ago, leaving their shredded remains as this diffuse glow. If it's dust, that points to more recent, violent collisions still shaping the galaxy today. Either way, this faint infrared whisper holds clues to the forces that built and continue to reshape one of the universe's most enigmatic galaxies. Now let's pull back the curtain on another perplexing mystery at the heart of Centaurus A, the enigma of its supermassive black hole spin. You'd think measuring how fast a black hole rotates would be straightforward, but when it comes to this cosmic giant, astronomers keep getting conflicting answers. Some studies suggest it's spinning at nearly the speed of light, while others indicate a much slower rotation. So what's causing this cosmic disagreement? One major hurdle is the black hole's warped surroundings. Imagine trying to gauge the speed of a merry-go-round while peering through a foggy, twisted lens. That's essentially the challenge scientists face. Centaurus A's black hole is shrouded in thick dust lanes and surrounded by a turbulent accretion disk that might not be flat, but instead bent or tilted from past collisions. This warping distorts the X-ray and radio signals we use to measure spin, making it seem faster or slower depending on which part of the disk we're observing. Some researchers argue these irregularities could explain why different teams get wildly different spin rates, like cosmic optical illusions skewing our view. Then there's the issue of measurement limits. Pinpointing a black hole's spin relies on detecting subtle fingerprints in high-energy light emitted near its event horizon, a region where gravity warps space so severely that even light struggles to escape. But our telescopes might not yet be sensitive enough to catch all the nuances. It's like trying to decipher a whisper in a hurricane. the finer details get drowned out by the black hole's own overwhelming noise, its jets, radiation, and swirling matter. Current technology might only reveal part of the picture, leaving room for competing interpretations. Could something even stranger be at play? A handful of theorists propose that Centaurus A's black hole might not have a consistent spin at all. If it devours another black hole during a merger, a real possibility given this galaxy's violent history, the collision could leave it wobbling like a top losing balance with its spin axis tilted chaotically. This wobble could make the rotation speed appear to change depending on when and how we observe it, adding another layer to the mystery. Why does this spin debate matter? A black hole's rotation isn't just a cosmic trivial fact. It shapes how the monster feeds, how its jets form, and even how it influences the entire galaxy's evolution. Faster spinning black holes launch more powerful jets, potentially heating up surrounding gas and stifling star formation. If we can't pin down this basic property, our understanding of Centaurus A's past and future remains fuzzy. The silver lining: next-generation telescopes, like the upcoming European space mission Athena, are designed to peer deeper into these spinning enigmas with unprecedented clarity. Soon we may finally cut through the confusion and see Centaurus A's black hole for what it truly is, a whirlpool in spacetime spinning its own cosmic tale. Now let's shift our gaze to one of the most daring theories about Centaurus A's supermassive black hole, the idea that it might be a cosmic fugitive, once flung from its home during a violent merger before being dragged back. This wild scenario, known as the runaway black hole theory, sounds like science fiction, but some astronomers argue there's tantalizing evidence to consider. First, let's unpack how a black hole could go rogue. When two galaxies collide, their central black holes eventually spiral toward each other, locked in a gravitational dance. If they merge, the resulting black hole can recoil from the enormous energy released in gravitational waves like a cannon firing backward. In extreme cases, this kick could be strong enough to eject the black hole entirely, sending it speeding into intergalactic space. But Centaurus A's black hole didn't escape forever. Instead, theorists propose it was reeled back in by the galaxy's gravity, like a boomerang returning to its thrower. So what hints support this dramatic story? One clue lies in the galaxy's peculiar structure. Centaurus A's dust lanes and stellar streams suggest a messy past filled with mergers, possibly involving multiple black holes. If one of those mergers ejected the current black hole, the recoil could explain why its jets appear slightly off-axis compared to the galaxy's disk, a telltale sign of a black hole that's still settling after being thrown off balance. Then there's the black hole's odd location. Some studies note it isn't perfectly centered in the galaxy, as if it's still drifting back to its rightful place. This misalignment is subtle but fits the idea of a black hole that was flung outward and is now slowly returning. Add to this the spin mystery we just discussed. An erratic rotation could be a relic of the violent kick that sent it flying. Not everyone's convinced, though. Skeptics point out that black hole ejections are incredibly rare, requiring a precise alignment of spins and merger conditions. Others argue that the observed offsets could stem from simpler causes, like uneven gas distribution or ongoing interactions with smaller galaxies, without direct proof. Like a trail of stars tracing the black hole's path, the runaway theory remains speculative. But that's what makes it thrilling. If true, it would mean Centaurus A's black hole isn't just a monster, it's a survivor, one that ventured into the void and fought its way home. The next time you look at Centaurus A, picture this: a titanic struggle, gravitational waves ringing like bells, and a black hole catapulted into darkness only to be pulled back into the heart of the chaos. Whether fact or cosmic folklore, this theory reminds us that even the mightiest objects in the universe are at the mercy of gravity's unyielding grip. Now let's turn our attention to another cosmic puzzle lurking in Centaurus A. an eerie, faint glow of gamma rays wrapping around the galaxy like a ghostly shroud. This mysterious emission, detected by NASA's Fermi Gamma Ray Space Telescope, isn't confined to the galaxy's core or its jets. Instead, it forms a vast, diffuse haze stretching far into intergalactic space. So what's casting this high-energy glow? Astronomers are locked in a spirited debate, with two leading theories vying for dominance. The first points to dark matter, that elusive substance making up most of the universe's mass. If dark matter particles collide and annihilate, they could produce gamma rays, and Centaurus A's massive dark matter halo might be the perfect site for such events. Supporters of this idea note that the haze's smooth, widespread distribution matches predictions for dark matter decay. If proven, this would be a groundbreaking clue in the decades-long hunt to uncover dark matter's true nature. But there's another compelling explanation. The haze might be a relic of the supermassive black hole's past fury. Imagine outbursts from the black hole, erupting with such force that they blasted particles across millions of light years. Over time, these particles could interact with cosmic rays or magnetic fields, generating the gamma-ray glow we see today. This scenario would make the haze a sort of cosmic echo, a fossil of ancient violence. Intriguingly, similar gamma-ray halos have been spotted around other active galaxies, hinting at a common process tied to their black holes, the challenge. Both theories fit the data for now. To settle the debate, scientists are scrutinizing the haze's precise energy signature. Dark matter collisions should produce gamma rays at specific energies, while black hole outbursts would create a broader spectrum. Future telescopes like the upcoming Cherenkov Telescope Array could provide the resolution needed to crack the case. For now, the gamma-ray haze remains one of Centaurus A's most tantalizing mysteries. Whether it's a whisper from the unseen dark matter or a roar from the black hole's distant past, this eerie glow reminds us that the galaxy's secrets aren't just written in starlight, they're etched in the invisible, high-energy currents flowing through the cosmos. Now imagine a cosmic fire hose that sometimes blasts water at full force and other times sputters unpredictably. That's essentially what's happening with the jets shooting out from Centaurus A's supermassive black hole. These jets, which stretch across millions of light years, don't just pour energy steadily into space, their output swings dramatically, leaving scientists scratching their heads over what's driving these wild fluctuations. At the heart of this mystery is the black hole's feeding frenzy. Like a messy eater, it doesn't consume gas and dust at a steady rate. Sometimes a dense cloud of material falls into its grasp, fueling a sudden surge in jet activity. Other times, the inflow slows to a trickle and the jets dim as if running on empty. But here's the twist: the changes in jet power don't always match the amount of material falling toward the black hole. This mismatch suggests something else is at play, something like magnetic reconnection, a process where magnetic field lines snap and rearrange like rubber bands stretched too far. When this happens near the black hole, it can release bursts of energy that supercharge the jets without any extra food being consumed. Adding to the intrigue, observations reveal that the jets aren't just fluctuating in brightness, they're also changing structure. Bright knots form and fade within them, hinting at internal shock waves or instabilities. Some researchers think these knots could be caused by clumps of gas getting caught in the jet's flow, while others argue they're the aftermath of magnetic explosions near the black hole. Either way, these variations make Centaurus A's jets some of the most dynamic and unpredictable features in the galaxy. Why does this matter? Because these jets are cosmic accelerators, slinging particles to near-light speeds and shaping the galaxy's surroundings. Their erratic behavior influences how energy spreads through intergalactic space, potentially triggering or stifling star formation in distant gas clouds. Understanding their swings could even shed light on why some galaxies flare up as quasars while others stay quiet. The next leap in solving this puzzle will come from telescopes capable of catching these changes in real time. Instruments like the upcoming square-kilometer array radio telescope could monitor the jet's flickers almost like a cosmic heartbeat, revealing whether their tantrums stem from messy meals, magnetic tantrums, or something even stranger. Until then, Centaurus A's capricious jets remain a high-energy enigma, reminding us that even the universe's most powerful engines have their off days. Now let's turn our gaze to the ghostly rivers of stars silently streaming into Centaurus A. These faint, wispy trails of light aren't just random scatterings. They're the cosmic fingerprints of smaller galaxies torn apart by Centaurus A's immense gravity. Imagine a spider's web capturing flies, but on a galactic scale. Over billions of years, as these doomed galaxies drifted too close, Centaurus A's gravitational pull stretched them into long, shimmering strands of stars, now weaving their way into the larger galaxy like celestial rivers merging into an ocean. What makes these stellar rivers so fascinating is the story they tell. By mapping their paths and measuring the speeds of their stars, astronomers can piece together the identities of the galaxies they once belonged to. Some streams trace back to dwarf spheroidal galaxies, small, faint collections of stars that orbited Centaurus like moths around a flame. Others hint at more dramatic encounters, like spiral galaxies whose delicate disks were shredded during close passes, leaving behind ribbons of stars as the only evidence of their existence. One of the most striking examples is a vast arc of stars curving around Centaurus A's outskirts, likely the remains of a galaxy at least 100 times smaller than its captor. The stars in this stream move in a synchronized flow like a school of fish, their shared motion betraying their common origin. Chemical analysis adds another layer. These stars often have distinct metallicities, lower amounts of heavy elements compared to Centaurus A's native stars, revealing they were born in a more primitive, less chemically enriched galaxy. But the detective work doesn't stop there. Some streams show signs of kinks or bends, suggesting they've interacted with dark matter clumps or other unseen structures as they fell inward. Others appear unusually thin, indicating their parent galaxies were probably gas-poor and fragile, dissolving easily under tidal forces. A few even crisscross, painting a picture of multiple mergers happening at different times, like layers of sediment recording geological history. These rivers aren't just relics of the past, they're shaping Centaurus A's future. As their stars gradually mix with the galaxy's main population, they bring fresh stellar diversity and may even spark new star formation when their gas collides with Centaurus A's own reservoirs. For astronomers, these streams are like time machines. By studying them, we can reconstruct a timeline of Centaurus A's meals, understanding how it grew so massive and what kinds of galaxies were common in its cosmic neighborhood billions of years ago. The next time you see an image of Centaurus A, look beyond its dusty lanes and glowing core. Those faint, delicate rivers of stars are silent witnesses to a dramatic history of galactic survival, and a reminder that even in the vastness of space, nothing ever truly disappears without a trace. Moving beyond the silent rivers of stars, we now tune into the whispers of the past radio echoes that reveal Centaurus A's hidden outbursts. These delayed signals are like cosmic voicemails, carrying secrets of the galaxy's violent history encoded in their wavelength. When the supermassive black hole at Centaurus A's core erupts, it doesn't just send jets racing outward in a straight line. Some of that energy bounces off interstellar clouds, dust, or even the galaxy's own magnetic fields, creating faint echoes that reach us years or even centuries after the initial blast. Astronomers have turned these echoes into a powerful tool. Imagine shining a flashlight into a foggy night. Some light beams forward, but some scatters back, illuminating the haze around you. In the same way, radio telescopes catch these scattered signals, peeling back layers of time to reconstruct past eruptions. One striking example comes from the galaxy's giant radio lobes. While the lobes themselves glow with active jets, subtle ripples and filaments within them match predictions of older outbursts. By comparing the brightness, shape, and polarization of these ripples to modern jet activity, scientists can estimate when the original explosion occurred and how much energy it unleashed. The most fascinating echoes, though, come from structures called light echoes in radio wavelengths. Just as sound echoes fade over distance, these signals weaken as they travel, but their delay patterns are precise. For instance, a jet might flare in 2020, but its echo could hit a dust cloud 50 light-years away and return to us in 2070. By modeling these paths, astronomers have uncovered evidence of a colossal outburst from Centaurus A's black hole around 300 years ago, one that would have outshone the entire galaxy in radio waves. But the real magic lies in the details. Some echoes show unusual twists in their polarization, a sign they've skimmed past magnetic fields or dense gas clouds, subtly altering their journey. Others appear smeared or distorted, hinting at turbulent regions near the black hole where particles are whipped into frenzy. There's even a theory that echoes might reveal missing eruptions periods when the black hole was hyperactive, but Earth-based observers lacked the technology to detect them. These echoes aren't just about the past, they help predict future behavior too. By studying how often Centaurus A's black hole erupts and how those eruptions evolve, astronomers can refine models of galactic-scale feedback, the process where black holes regulate star formation by alternately heating and disrupting surrounding gas. Every echo is a piece of the puzzle, showing how Centaurus A's violence shapes its own destiny. So the next time you hear static between radio stations, think of Centaurus A. Those faint crackles might not be random noise, they could be the faint, delayed whispers of a galaxy's explosive past, still traveling across the cosmos to tell their story. Now, let's shift our focus to one of the most puzzling gaps in our understanding of Centaurus A, the mystery of its dark matter, clumpiness. Simulations of cosmic structure tell us that galaxies like Centaurus A should be surrounded by countless smaller pockets of dark matter, like invisible satellites orbiting a massive host. Yet when astronomers scan the galaxy, they find far fewer of these substructures than theory predicts. This discrepancy isn't just a minor hiccup. It could force us to rethink how dark matter behaves or even how our telescopes perceive the unseen cosmos. So why does this matter? Dark matter doesn't emit light or interact with normal matter electromagnetically, but its gravitational influence is undeniable. It's the cosmic scaffolding that shapes galaxies, and its substructures, smaller clumps within the larger halo, should leave subtle fingerprints. For example, they'd slightly warp the paths of stars or bend background light through gravitational lensing. In Centaurus A, though, those expected distortions are oddly sparse. Some regions that simulations flag as dense with dark matter appear eerily smooth in observations. One explanation could be technological. Our current telescopes might simply miss the faintest, smallest clumps. Just as a fishing net with wide gaps lets tiny fish slip through, our instruments may lack the resolution to detect the tiniest dark matter knots. The Hubble Space Telescope and ground-based observatories have spotted a few dwarf galaxies around Centaurus A, potential tracers of dark matter, but their numbers fall short. Future telescopes like the James Webb Space Telescope or the upcoming Vera C. Rubin Observatory could change this, peering deeper into the galaxy's outskirts with unprecedented sensitivity. But there's a more radical possibility. Perhaps dark matter isn't as clumpy as we've assumed. Most models treat it as cold, meaning its particles move slowly, allowing dense structures to form easily. If dark matter were slightly warmer, its particles zipping around faster, it'd resist clumping as tightly, smoothing out the substructure we expect. Alternative theories like self-interacting dark matter where particles bump into each other could also erase smaller clumps over time. Centaurus A's unusually tidy halo might be a clue that dark matter's behavior is more complex than a simple, sluggish shadow. The stakes here are high. If the missing clumps are real but unseen, it's a challenge to our observational tools. If they truly don't exist, it's a challenge to fundamental physics. Either way, Centaurus A's dark matter puzzle reminds us that the universe's greatest mysteries often lurk in the gaps between prediction and observation, waiting for the next leap in technology or theory to bring them into focus. As we approach the final mystery of our cosmic journey through Centaurus A, let's turn our gaze to the distant future. What fate awaits this galaxy with its violent past and turbulent present? The answer lies in the interplay between its monstrous black hole and its appetite for galactic mergers. Right now, Centaurus A is a powerhouse, its supermassive black hole spewing jets that sculpt the surrounding space. But over billions of years, those furious outflows may quiet down, or explode with even greater fury. It all depends on how much gas and stars the galaxy continues to devour. If fresh mergers funnel more material toward the black hole, it could awaken as a quasar, one of the brightest objects in the universe. Imagine a beacon so intense it outshines its entire galaxy, fueled by infalling matter heating up to millions of degrees. Yet there's another path. Without new mergers, the black hole could starve, its jets fading as it runs out of fuel. The galaxy might then enter a dormant phase, its star formation slowing until only aging red giants and white dwarfs remain. This would leave Centaurus A as a sterile giant, a quiet relic of past fireworks. But there's a twist. The Milky Way and Andromeda are on a collision course, and their merger will one day send our combined galaxy hurtling toward Centaurus A. When that happens, the resulting cosmic pileup could reignite Centaurus A's black hole, turning it into a quasar once more. Or, if the merger is messy enough, it might scatter the remaining gas, leaving behind a dark, quiet behemoth. The wild card is dark matter. If Centaurus A's halo is as smooth as observations suggest, future mergers might unfold differently than in other galaxies. Its strange lack of substructure could mean fewer satellite galaxies to consume, altering its growth trajectory. No matter which path it takes, Centaurus A's story is far from over. It reminds us that galaxies, like stars, have life cycles, eras of chaos, brilliance, and eventual transformation. And while we can't watch its fate unfold in real time, every clue we gather today helps paint a picture of tomorrow's cosmos. One thing's certain, the universe always has surprises in store. Now that we've explored all 50 strange phenomena, from its warped dust lanes to its enigmatic dark matter, one truth stands clear. Centaurus A isn't just another galaxy, it's a cosmic laboratory, challenging our understanding of how the universe works. If you've enjoyed this journey through its mysteries, don't forget to like, subscribe, and share your favorite phenomenon in the comments. The cosmos is full of wonders, and we're just getting started. As we bring our journey through Centaurus A to a close, let's take a moment to marvel at just how much this galaxy has shattered our expectations. From its supermassive black hole with tangled magnetic fields to its ghostly stellar streams and unexplained gamma-ray emissions, every corner of this cosmic enigma has challenged what we thought we knew. Galaxies aren't supposed to have polar rings or counter-rotating gas disks, yet Centaurus A flaunts them with defiance. It shouldn't blast gamma rays while hiding its core behind dust, yet it does. And while most galaxies follow predictable life cycles, this one keeps rewriting its own rules with every merger and outburst. What makes these 50 phenomena so extraordinary isn't just their strangeness, it's how they force us to rethink the fundamentals of astrophysics. Take its missing globular clusters. Most galaxies of its size should be surrounded by hundreds of these ancient star clusters, but Centaurus A has shockingly few. That gap hints at a history so violent it ripped apart entire systems, leaving behind only echoes. Then there's the paradox of its star formation, raging near the black hole's chaos while other regions lie eerily quiet. It's as if the galaxy can't decide whether to create or destroy, leaving astronomers scratching their heads. But perhaps the biggest lesson Centaurus A teaches us is humility. For every mystery we've unraveled, like the origins of its warped dust lanes or the power behind its radio lobes, dozens more remain. Why does its gamma-ray output flicker unpredictably? What's the true nature of those ultra-fast hydrogen clouds? And is there really a hidden dwarf galaxy tugging at its stars? Each question reminds us that the universe is far stranger, far more inventive than our theories can yet explain. This galaxy isn't just a spectacle, it's a roadmap. By studying its contradictions, we're piecing together how collisions shape galaxies, how black holes govern their homes, and how dark matter silently pulls the strings. Every oddity, from its green valley status to its X-ray jet knots, adds a puzzle piece to the grander picture of cosmic evolution. And while Centaurus A might be one of the closest giant galaxies to us, its secrets resonate across the universe, offering clues about how all galaxies grow, change, and fade. So as we sign off, remember, the cosmos is brimming with enigmas waiting to be discovered. Whether it's the next oddity in Centaurus A or a mystery in some distant corner of the sky, there's always more to explore. If you've enjoyed this deep dive into the galaxy's strangest quirks, let us know in the comments which phenomenon fascinated you the most. And don't forget to like, subscribe, and hit that notification bell, because the universe never stops surprising us, and neither will we. Until next time, keep looking up. The next cosmic revelation could be just over the horizon.